Okay, we should be broadcasting to a YouTube video. I'm going to check the YouTube site now just to confirm. To a YouTube video. I'm going to check the YouTube site now just to confirm. Okay, that looks like it's working. I'll check it again right before we get started. It's 11:48, so we have some time. I'm going to send the link out to the UNC folks first. Okay, I sent the link out to the committee. We'll see how long it takes for you all to respond. That would give me an idea of how much time is typical between sending the email and getting someone to respond. Just going to check again. Hey, just going to check again. No, I just sent you a new link. Okay, sounds good. Bye. Okay, sounds good. Bye. Okay. Seems to be recording. Be back in a minute.
Hello? I don't know if it's sound. I don't know if I have sound.
Well, there's no one there to say anything.
I know, but it wasn't even ringing. I haven't heard anything.
Well, it would have connected immediately because it was already set up.
I'm a little worried. I don't have sound.
No, I'm here.
Ah, there
Oh,
we go.
hello.
Go.
Okay, I do have sound.
Okay.
Yeah. I'm just making some tea.
Okay.
Okay.
And we can see you. Hello, Dan.
Hello, Dan.
Yes, I turned it around. So. Okay, you're in the conference room. That's good.
Yep, we're just.
I'm just going to the restroom.
Okay. That was pretty good.
And everything's recording. I'll be back with my tea.
Hello, Nick. Can you hear me?
Hey, Chuck. Yep.
Hey, good. It works.
You're a little quiet, but that's probably a problem at my end.
Okay.
Maybe not.
I'm using headphones. Does that make any difference there?
No. It's probably maybe just the laptop that we're using. Well, we can hear you.
Okay. As soon as Dan comes, I don't know who's in the middle there.
That's Dan.
Okay.
He's just making tea.
There he is. Hey, Dan.
Yeah.
How's my microphone sound?
Sounds great.
Okay.
Now, I'm not using my earbuds, but I'm not hearing any feedback or anything on my side. Everything seems.
I've got mine on.
Yeah, it's fine. That's good.
I'm not sure how many people are coming to this room. I don't know. I guess John would be the other person. I don't know if he's going to come. I think so.
I think he said he's
Nick,
coming today.
Oh, he's not today? Okay.
Nick, you have a little bit of behind you illumination from the window. I don't know if you have any options.
Is that better?
It's better, but it's still pretty strong. I don't know if you've got the ability to swing the camera a little bit
To the right.
further to the right, looking more toward the door. Yeah, that took the window out of the field of view.
Okay, that's fine.
I don't know how it's going to be as far as seating and all that, but
I'm sure we can figure it out.
Yeah, it's out of the reduced field of view, but not the broader field of view. But I can see your face just fine.
Okay.
Actually, right now it's illuminating your face a little bit. So some of the other windows, I guess. So you're not silhouetted.
Okay, good.
In fact, opening the one that looks out over the parking lot might be good for illuminating it.
Yeah, and also having the lights on in here. I'll open the other ones.
We have all those great astrophotography images on the wall too.
Yeah.
Well, there it's a matter of finding every single little LED in the dome and covering it over.
We should tell the candidates that we're showing off some of our SOAR telescope pictures in the background.
That's right. Look at the rings on that planet.
we use the AO system to get that precision image of Saturn there.
Right. Oh, those rings look pretty sharp to me.
Yeah. So I wrote my intro out as a script to make sure I say the same thing to all the candidates. And Hopefully I'll read through it without bumbling it too much and making it sound natural. Okay, I'm gonna email Brooke. Brooke Simmons is first.
You want to be here? You want to be there? Where do you want to be?
I'm fine here.
Okay.
If John doesn't come, then we'll, yeah, we'll make it look like we don't have just a suspicious gap.
This looks pretty good.
Okay, I sent the link. Hopefully this all just works.
It's cold.
Is it cold there?
It is cold.
Yeah. They may actually turn down the heat during the break.
It's always cold in the labs.
Yeah, they definitely do that. I can confirm from previous years.
Yeah, combining that with the fact that that room is
It's always cold. in that.
always cold. How are your hands?
They're pretty good. Underneath the gloves, they're almost back to normal. And when I hold them up here, they look totally normal. Down below heart level, they get really red. Hence the need for the gloves, I guess. And I think I have to wear them for 4 or 5 more months, plus or minus.
Wow.
Then we'll see. Okay, I think we have Brooke here.
Hello.
We can hear you. Can you hear us?
I can hear you, yes.
Okay.
Actually, I cannot hear.
Oh, you cannot.
You can't hear me?
What about Nick and Adrian? Can you hear?
Yes,
We can hear Brooke fine.
we can hear Brooke fine.
Hi, Brooke.
Okay. Hello.
Chuck,
I hear it, by the way.
you do? Okay, good.
Yes.
So you're our first one. So we're trial shooting the technology here. So we'll see how it goes. If
Got
there-
it.
just bear with us. We'll figure
Did
it
we already
out.
start recording?
Yes. Yeah, we started recording
Great.
before you even came in. So yeah, it's being recorded. But as I said in the email, it's just in case we want to go back and
Okay.
take a look at things to help us make decisions.
Oh, yeah. This is by far the most convenient way to record a group conference like this, even if you never intend to publicize it. I've done it many times.
Okay, good, good. Yeah, it's my favorite way as well. Well, thanks for meeting with us today. And I figure we'll start with some introductions. Then I'll give you a little formal speech so you know what we're expecting today. I'll start with myself. I'm Dan Reichert. I'm chairing the search committee this cycle. And my focus is small robotic telescopes, originally gamma ray bursts, though these days I'm more interested in the technology of bringing this capability to a broad audience, both for research and education. And let's just go across the bottom. We have the group cluster room at UNC. Want to go left to right? Nick?
Hi, I'm Nick Law. I'm an assistant professor, and I work on exoplanets and general time domain astronomy, building instruments for very small telescopes and fairly large telescopes for time domain astronomy follow-up.
I'm Adrian Erichek. I'm also an assistant professor, and I do theoretical cosmology.
Okay.
I'm John Engel. I'm a professor. I'm not an astronomer. I'm theoretical nuclear physicist. But on the committee is, an external person. I'm in the
Okay,
department
great.
field.
Right.
And
I
I'm
do something related to our process, nucleosynthesis, but not from the astronomy side.
Chuck Evans. I'm a gravitational physics theorist, interested in modeling sources of gravitational radiation, and been involved in the SOAR project for a long time, 20 years.
Oh, okay.
Yeah, they actually began SOAR initially when I was 12 years
Right.
old, so it's been a long project. Not that I'm implying Chuck was there at the beginning. So
Not quite.
I should say I'm getting over like a Christmas cold, so I apologize for the coughing.
oh, that's okay. I think a number of us are suffering. I a little bit. Anyway, so the primary thing that we want to hear from you today is an overview of your vision for a research program here at UNC, organized by research topic. So for each topic, we'd like to hear a brief overview of the science and why it's important. So we, of course, got a lot of that from your application. So let's
Right.
focus also on how our resources fit into your plans. And by resources, I mean our observational resources, our computational resources, if relevant,
Right.
and our people, be it grad students, undergrads, or postdocs you may hire. Now, that said, we don't expect you to be an expert on all of our facilities at
Okay.
this point. So we're hoping that you'll engage us with questions as you go along. We want this to be less of a presentation and more of a conversation where we're here to help you fill in some of the UNC specific details. So let's spend about 15 minutes on
Great.
what vision, and we'll save the final 5 to 10 minutes for follow-up questions and questions you may have. Sound good?
Okay, great. Yeah, that sounds great. So I guess to start, I think the broad general thing to say is I work on galaxy evolution, and I particularly work on the coevolution of black holes and galaxies, but not only on that. So I'm the deputy project scientist for Galaxy Zoo, and as part of that, I work on a lot of different galaxy evolution projects, which basically tie morphology to the physics of galaxy dynamics and so on. Examine galaxy evolution over many different redshift ranges and so on. That includes sort of your standard survey kind of work where you're taking a large population of galaxies and maybe cutting it into pieces, slicing it in different ways, controlling for different things, and then examining trends over long over masses or over redshift over long baselines of time. So I will continue to work on that. I think one of the great things about actually LSST is that it's available to anybody in the US. Everyone in the US has data access to LSST once it starts operations. So that's going to be a real benefit no matter where I end up. But actually SOAR has a lot of great properties. It's a really good telescope and it's very well placed. For follow-up, it's hard to predict exactly what that's going to be, but I can talk about some specific examples. So some of the work that I do is in black hole galaxy coevolution, you end up with fairly small samples because I became, over the past several years, I became really interested in the merger-free evolution of galaxies. That is, what happens to galaxies and their central black holes in the absence of the mergers that, at least as of a few years ago, had been kind of considered to be the general way the galaxies grow over time. Of course, now we know that there are things like cold accretion that can happen that can grow galaxies to Milky Way sizes or even bigger in the absence of mergers. And it turns out that those are a very significant pathway to growing both galaxies and black holes. And that's through various types of work I've done. I did a meta-study in 2012 with some colleagues of mine, and so it's 5 years ago now. Meta-studies are always a little bit fraught, but it actually has held up pretty well. That mergers are maybe half of the picture of the growth of black holes in a cumulative sense. Looking today at more advanced simulations, we've recently submitted a paper with that's been led by a graduate student at Hertfordshire, and it's using the Horizon AGN simulations. Actually finds that mergers are only maybe 35% of the overall growth of black holes. Since redshift, high 20 or something is when that starts. So the merger-free picture is not well understood, but it's clearly important. So I began looking for galaxies that had grown, the whole length of the universe without ever having a merger. And you do that by looking at the morphologies, because mergers above a certain size, like 10 to 1, they tend to inevitably create bulges. And so if you look for a disk galaxy that hasn't got a bulge, or has a very, very small bulge, you can say that it really hasn't had a history that has any significant mergers in it. The first time I did that selection was a pilot selection. We took all of Sloan, and I selected 13 galaxies. It turned out my selection was extremely conservative, so I went back and did a slightly different one. And I got about 130. So this is an interesting sample to work with, because it's this realm within surveys where you get enough objects to say something useful, but it's not like you have thousands and thousands to play with. And yet they're really probative. They're very interesting. So I wrote a paper that came out this year that showed that these galaxies, the black holes in these galaxies, are actively growing. They're growing at quasar-like luminosities, many of them. And their black holes are sort of normal supermassive black hole masses. They're much higher than you would expect, even based on quite conservative upper limits to the bulges of these galaxies. And we only had upper limits on the bulges because we were using Sloan data. So not AO by any means. AO would actually really help with these. But just sort of, terrible seeing and, fine, but we put upper limits on it, and it still showed this result. We then went and got a snapshot survey that I'm leading. We have 96 orbits observed, and we might get a couple more, but it's basically finished. So we got just under 100 orbits. I'm calling that survey Magnus for reasons, we're terrible at naming things, but that was the best I could come up with. It has AGN in the title. And the goal of that is to do very high resolution bulge disk decompositions. These are galaxies with redshifts like less than 0.25. So Hubble really gives you very good resolution. And for the nearer ones, you can even maybe see nuclear star clusters. So the main point of that survey is to be able to map black hole galaxy coevolution as a function of merger history, because by understanding what the bulges look like, we can understand what the merger histories have been.
So
But that's sort of my plan for the next few years. And I've actually been running a long-term LIC campaign to do follow-up on those using the Shane 3-meter telescope, which doesn't have quite the resources that SOAR does, but it still has been useful. And I think SOAR would be a really great way to pick up and then continue on with some of the other stuff. So for the next couple of years, few years, that's going to drive a lot of my work. And particularly, there's at least one PhD thesis in there, and I think there's work for a postdoc in there too. For example, it's a very rich data set. One of the examples is that 2/3 of these galaxies unexpectedly have very strong signs of nuclear outflows. And we don't really the outflow, the kind of outflows in AGN in a regime where there haven't been any recent mergers, and so the geometry is different in the system. Those aren't very well studied, and we need to look at those. I've started looking at, I've got a program, it's in a few months. In April, we're going to be looking using the narrowband filter set they have at LIC, but that's not really ideal. I think something more like the IFU that's on SOAR would be ideal for looking at these outflows. And so that would be a really strong part of a plan in the near term.
So let me.
We just found out a couple.
Oh yeah, and sorry to interrupt. I just want to get in my head because I'm not a galaxy. So the sample,
right.
Magnus sample, is selected from your SDSS sample.
Right.
That is sampled. You're looking for large bulges with high luminosities. Is that the criteria?
We're looking for large disks and no bulges. Or very small bulges. Some of them have small bulges. Yeah. Sorry. So they're disk-dominated galaxies. So the disks have never been disrupted by a merger. And some of them have maybe some signs of like a minor interaction, which is really interesting, and that goes to something else I'll talk about. But yeah, so that they're selected from Sloan, but right now what I'm working on is using things like SkyMapper, and as soon as it becomes public, DES, to do the same thing in the south, because this is in a regime where even doubling the sample set is really important, and we'll be able to do a lot more with that and tease out some of the more subtle effects. So that'll be only some of the sources are going to be visible from SOAR, right? I don't know exactly what fraction of Sloan is visible from where SOAR is, but still some of them will be, and then the ones in the south certainly will be. So does that answer your question?
Mm-hmm, mm-hmm.
Okay, great.
You've been using a 3-meter telescope, Shane, and for that it's spectroscopic follow-up?
Yep, these are very bright sources, so it's not a problem. I've been able to get really good long slit spectra on these in like an hour on the Shane. So you could easily do a survey of 100 objects. It wouldn't even take that long with something like SOAR. With IFU especially, I think it would be fine.
So I assume these are all very...
They're out to about 0.25. Yeah, so they're pretty local.
Okay.
Yeah. I think once we move into other surveys, when like Euclid goes public and when LSSD has its sort of better seeing nights that are stacked up enough to be able to do the morphologies well, I think we'll be able to go to higher redshift, but I think it'll still be well within reach of a 4-meter telescope. So then the thing that we just found out about a couple of weeks ago was we had a program that we applied for the gap filler program with HST. There are certain RA hours and some windows that don't get very well sampled by typical HST proposals. And so there was a call for proposals that would fill those gaps and with a large sample. So we proposed in Galaxy Zoo to explore what we call the gems of Galaxy Zoo. But really what it is the kind of known unknowns. That is, Galaxy Zoo, because it has lots of human eyes, and particularly lots of like novice human eyes that don't know where to look, so they look everywhere and they ask the kind of obvious questions. We get a lot of interesting discoveries in Galaxy Zoo and things that turn out to be important, like the ionized clouds that are very far extended from black holes that have since switched off. We call them Voorwerps because the Dutch school teacher who discovered them called them a Voorwerp, which turns out to, I hope nobody there speaks Dutch because I think I'm butchering the pronunciation, but they turn out to mean thingy. That's what that word means. But we have a collection of these Voorwerpies, and they're really interesting as they help, you can kind of map out the luminosity and the variation in individual black holes over tens of thousands of years, because that's the scale, tens of thousands of light years of these clouds. So that's one example of a discovery. Another one is the so-called green peas, which are these very compact, extremely high star-forming galaxies that we think are local analogs of high redshift star-forming galaxies. They haven't been well studied with HST very particularly, and certainly not at moderate redshift. And there are lots of other examples that like individually wouldn't have made a terribly strong case for an HST proposal on their own, but in aggregate, we know we're going to get discoveries out of it. And we were one of 3 proposals that was accepted for that gap filler proposal, and we're going to get about 300 orbits out of it. So that was a very pleasant surprise. I'm going to be pretty strongly involved in that. One of our target samples is looking at radio AGN, so AGN with jets that are in disk-dominated spiral galaxies. Our understanding of what forms radio jets in the first place. So we want to understand a lot more about those, and getting high resolution imagery is a first step, but actually getting spectroscopic follow-up along many, like polarization, there's going to be a lot of interesting things to follow up with those. And we've just so far looked at them in like FIRST and WISE. So there's not very high resolution imagery even, and there's certainly not great spectroscopy of those yet. So it's going to be a huge an area to follow up. And again, they're pretty nearby, so SOAR is really going to have no problem with those. There's going to be a lot of interesting edge cases.
Now, what do you get specifically from the spectrum?
Sorry, say again?
Sorry, there's a little bit of lag.
Yeah.
Yeah,
no, it's fine. I think it's probably me because I'm kind of in the countryside of France, so the Wi-Fi is, it's pretty good. Well, so I think from the spectroscopy, we'll get not just information about the gas dynamics and the stellar dynamics of the regions around the black hole, but if we look at the polarimetry, we might be able to understand more about what's happening magnetically in these objects, which obviously is pretty important. And that gives you different information from the radio information. So I'm going to be working with some of the Radio Galaxy Zoo, those collaborators there in Australia. So it's all Southern Hemisphere work. So that's why it's really well placed to work in with SOAR. So we can help kind of understand how these things can form in a galaxy that hasn't had some of the processes, the merger-driven processes that we think help to create jets. So we haven't started taking the data on that yet, and I don't think we are going to start getting the data on that till the next HST cycle, and it's meant to be a 2-cycle proposal. So that won't even really start getting good data in for another couple of years, which places it really, really well in terms of timing to come after the Magnus survey. We don't have a name for that second survey yet. We've literally not finished making the target lists. but that's going to be sort of 2 to 5 years is kind of a long-term plan. At the same time, we're also working on, in the larger context of the Zooniverse, I run the analysis group in the Zooniverse, which is roughly speaking the data science branch of the Zooniverse. We deal with a lot of interesting data problems, and we deal with a lot of interdisciplinary teams, teams from different sciences, and teams that are genuinely like computer scientists working with ecologists and so on. And our data is a little bit unique. So we help people work with the data, get the best results out of the data. And most of that is the code that, that I've already written that is on a repository that I maintain within the Zooniverse. And one of the big pushes in the Zooniverse that we've all been working on is preparing for the future of surveys like LSST, like WFIRST, like Euclid. We have not quite reached the big data era yet in astronomy. Particle physics is there, but LSST is going to be one of the first kind of forays really into proper big data in astronomy. And the techniques that we use now to do sort of basic morphological classification, and other kinds of classification as well, they're not going to scale that well. So we have been working on for quite a while doing this faster and more accurately by introducing machines into the classification. So for example, in Galaxy Zoo, we've run a test where we have a more intelligent classifier combination with human classifiers, although you can use machines too, that helps us get about a factor of 4 or 5 faster the same results using just this algorithm. And we've basically rerun it on a previous iteration of Galaxy Zoo to show that we get the same or better answers. But then once you add a machine on top of that, the idea being that you start the classification theoretically in a set of data where you don't have any information to start training the machines. Like you don't have a big set of data to start training the machines to start. And so you let the humans classify until you do have a good training set. And then you let the machines go. And this is, I mean, lots of people have done this so far. But the difference right now is that what we do is the machines classify what they can, but they always have a human to kind of verify. And part of that is because we always want to keep eyes on every image because we make interesting discoveries, especially when we have new classifiers looking at every image. But instead of having 40 people look at every image, we might only need 1 or 2. So that really significantly saves us time. And then as we train the machines, we continue to have the humans classify and we iterate between them. And so it's more proper human machine classification. And that actually turns out to get us better results in many ways at about a factor of 8 faster. And that is with a really basic, simple machine. So we can probably do better with better machines. This is just a random forest. It's not even something like a neural net. So that's an example in Galaxy Zoo. But this also applies quite naturally to things in the time domain. So we've been working on this for supernova classification. My colleague Daryl Wright, who was at Oxford, is now at Minnesota, has a paper on this for a project called Supernova Hunters, which uses Pan-STARRS 1 data that shows that the humans get they kind of slice the data one way, they're good at certain things, and the machines are good at a different set of things, and they're basically orthogonal, such that you get better and more accurate data and faster by using a combination of them. So all of this is leading us to LSST and surveys like it.
Okay.
LSST has invested pretty heavily, actually, in citizen science. So they're helping us to work on this, too. So I want to use that. Did you have a question?
I'm just watching the clock. I have lots of questions about Galaxy Zoom, though some of them will have to. I do want to give my colleague a chance to ask a few questions, then you a chance to ask questions about our facilities or anything at UNC.
Right.
So, Nick, Adrian, John, you have anything?
Yeah, so I was really interested in your ideas for SOAR, and it seems like the IFU would be really interesting for you. And we do have plans to have an IFU on the system, and it's in science verification mode at the moment.
Yeah, that's what it sounded like.
Mode, and only one mode is working. And I guess my question is, are there other instruments on SOAR that would be useful for you as well?
Yeah, I think there definitely are. I was really interested in, you have a RoboAO, is that correct?
We're in the process of building one.
Okay, I'm just going based off the website. I think it didn't necessarily say the stages that these were at. I mean, the AO is a really obvious case because just getting better resolution on some of the samples that we already have would allow us to do much better bulge disc decomposition, to kind of tease out some of the more subtle effects. Understanding it, because there's different kinds of bulge classifications and so on. Like when I give a full research talk, I talk in more detail about this. But to be able to identify those and pull those out useful, and doing that with AO is certainly possible. And actually, some of my colleagues at UCSD have been doing some really interesting work on using AO with IFU to disentangle AGN and Galaxy, which is interesting. But you don't need IFU, actually. You can do it with like a long slit. And maybe a multi-slit. I haven't used multi-slit that often, but that is still really, really very interesting. For example, for the outflows, IFU is sort of ideal for working for outflows, but you don't need them, right? You can use a fiber or a long slit spectrograph and identify them there, and then you can follow up with, say, a tunable filter set. I don't know what exactly is available on SOAR for that and at what redshifts you can tune to, but you can certainly do that with imaging in tunable filters. So all of that is possible. I think there's many different avenues that I would use SOAR for.
So what, when you say imaging and tunable filters, the thing that springs to mind immediately is the Fabry-Perot system, which is also under science verification mode. And that can be coupled with the AO system that is currently on SOAR, which doesn't get full diffraction limited resolution, but it can allow you to get kind of 0.3 arc-second resolution pretty routinely, which sounds like it could be nice.
That'd be great. That would be, I mean, that's a factor of about 4, better than what I have right now with Sloan and with Lick, because Lick doesn't get great seeing. So yeah, that would be really, really spectacular. Because a factor of 4 gets you pretty far out, so that would be excellent. I've not used a Fabry-Perot system, so I'd be really interested in speaking with you more about that and kind of jumping in. I think that'd be really, really interesting. And all that is really great for student projects as well, getting students really, well experienced with observing, as well as myself. I sort of love observing. So yeah, I'd be very, very interested in that. I should also say I didn't look into a huge amount of detail on the infrared capabilities for SOAR, but I do some work with some colleagues on dust-reddened quasars. We look at them in the infrared because they have some broad lines in the IR that in optical are not necessarily as broad, and you can learn a lot about them. They tend to be a little higher redshift as well. But I think a 4 meter is still pretty decent. You just have to integrate a little longer, but it's still definitely possible. So there's capabilities there, but I haven't looked into that in quite as much detail because it's stuff that I'm more like a co-author on. So
that, I think that could be a good match as well, in that the infrared spectrograph that will shortly be deployed on SOAR in the next year or two, Arconis, is a high efficiency infrared spectrograph.
Oh, great.
Basically a triple spec. So
great.
Yeah.
Yeah, that's what we use right now. We use triple spec on Palomar, so that'd be perfect. Excuse me.
Any other questions from committee members? And then I want to give just a quick opportunity for Brooke to ask us any questions, and then we'll need to cut it off in like 2 minutes. So
sorry, I spoke for. I have a lot of plans. It's almost too many.
If there are no other critical questions from the committee, let's give Brooke a chance to ask us questions, or any question that comes to mind.
So I wanted to ask you about teaching. I wanted to ask what a kind of typical teaching load is, and what courses you might be interested in me teaching, and whether they're to say create new courses or adapt courses that currently exist.
So the load is 1-on-1 for research active faculty. Has been ever since I've been here,
right.
And a little bit before as well, I think. And it's a little flexible. Sometimes we go 2 and 0 or 0 and 2, that kind of thing. And we have a wide selection of courses, and we try to match them to your interests. There will be an expectation of teaching at least one large mega section before, I believe, tenure or before full professor, one or the other. Everyone has to do that at least once. I love those. I try to grab as many as I can.
Those are fun, yeah.
Yeah. And I think many of us sitting here at the table have created a course since we've gotten here, and other people not at the table. So all sorts of things are on the table. We dull and mundane if you're not careful. So we try to present as many opportunities to liven it up as possible.
Okay, great. I've gotten really interested in data science, obviously. Data science is something that astronomers tend to learn naturally. This is a funny anecdote, but I was sitting in an airport, and this stranger sat right in sort of opposite me. And he was very chatty. I think he was a little nervous or something. He was an undergrad. He was on his way to a job interview, and it was like his first trip. But he was in computer science, and we got to talking. And at one point, he was asking me what I do. And he said, "Oh, do you do data science?" And I said, "Yeah, I do. What about you?" And he said, "Oh, no, you need a PhD for that." And I thought, why is that, right? I think the answer to that is that data science is not an extremely well-defined thing. One of the first things I said was like, am I a data scientist? What is data science? And I looked it up. There are various syllabus, like LSST has a data science like boot camp for grad students, which is a great idea. And yeah, you can go down and check off all of those things are things that I do. The reason that it takes a PhD, I think, in some respects, is that it's not something that anybody is driving towards, right? There's no PhD in data science. So you have to assemble that from multiple different fields. And I think that's a bit of a shame. Like, I feel like you could easily teach a course that would probably come just after like a computational physics course, data science, that would take those tools that you learn in a computational physics course and then apply them to larger data sets, to use statistical methods, to do visualization. And you could tune it to the like upper level undergraduate level or to the graduate level as well. And it would be not just extremely useful for people who wanted to do research in astronomy, because we have to use all those things, but it would also be really useful, in terms of being a public university, to teach people for skills that would be useful in industry. But I don't know what necessarily is already available there.
Also, because we're on our last minute, I need to wrap it up. But
oh yeah, sorry.
Based on what you were saying, I haven't been involved in this, though. I've been following emails. I believe your comment's very timely, because I believe we're in the process of creating a data science focused course. The rest of you cannot.
That's great. You're on the forefront then.
Yeah, that's right.
A graduate level course, if I recall.
Yep.
But anyway, we have
Great. Oh, I'd be so interested in teaching something like that.
It's going to happen at UNC. So
that's great.
Anyway,
I think you're the first. Well, I know that Yale is doing that. They're creating a data science major, but other than, I was visiting there because I was visiting. I was in the neighborhood. I was seeing my thesis advisor, and just randomly. But other than that, you're the first place I've heard that's actually doing that. So that's great. That's really good. Very beneficial for both us, for research, and for the students.
So many more things we could talk about, but unfortunately, we need to move on to the next one. Thank you so much for your time.
Thanks so much, you two. Really appreciate it.
Our pleasure.
Okay, got it. I'm posting the button. Okay.
Bye. Okay, I think that went good. Next up is Benjamin Montet. Let me get that email fired off. Okay. 12:30. Okay, so we're just running a couple minutes late. We'll try to pick it up if we can, but if we keep sliding, it's okay too. It just like it creates a minute or two of panic for these people on the other end waiting for their link, wondering if they're missing their interview. But think that went okay? Format wise?
Yeah.
Yeah.
Did you want to ask more questions? She was pretty chatty.
I tried to interrupt and throw some questions in there to try to make it more like a Here we go. So, Ben?
Hello.
Hey, so welcome.
Thank you.
Thanks for taking the time to meet with us today. So we'll begin with a round of introductions, and then I'll give you my introductory spiel so you know exactly what we're expecting.
Okay.
I'm Dan Reichert. I'm chairing the committee, the Astro Search Committee this cycle. My interests are small robotic telescopes, originally gamma ray bursts, though. That's what got me into it, but now I'm kind of more interested in those systems and making them available for broad use, research and education.
Okay.
And we'll go across our bar here at the bottom. So we have a room at UNC with 3 people there.
Hi, I'm Nick Law. I work on exoplanets, time domain astronomy, and instrumentation.
I'm Adrian Erichek. I work on theoretical cosmology.
I'm John Engel. I'm a nuclear theorist, not an astronomer, but work on our process, nucleosynthesis.
All right, great.
I'm Chuck Evans. I'm a gravitational physics theorist interested in modeling sources of gravitational radiation and been involved in the SOAR project for about 20 years.
Great.
All right. So the primary thing that we want to hear from you today is an overview of your vision for a research program here at UNC, organized by a research topic.
Sure.
So
Okay.
for each topic, we'd like to hear a brief overview of the science and why it's important. Of course, we got a lot of that from your application. So let's also focus on how our resources that we have at UNC, that we have access to, fit in with your plans. And by resources, I mean our observational resources, computational resources, if that's relevant, our people, our grad students, our undergrads, any postdocs you may want to hire. Now, that said, we don't expect you to be an expert on our facilities at this point. So we're hoping that you'll engage us with questions as you go along. We really want this to be more of a conversation, not so much a presentation, and where we're here to help you fill in details, at least UNC-specific details for your vision. So the plan is to spend about 15 minutes on what you envision for a research program here. And we'll try to save the final 5 to 10 minutes for follow-up questions from all of us, though hopefully there'll be interaction as we go as well. And a little bit of time for you to ask us questions that you may have about UNC.
Yeah, sounds great.
Okay, have at it.
I'm just going to hack a little bit. I'm getting over something here. So get that out before I start going. Yeah, so I am interested in stars and their planets. And in general, the overall architecture of planetary systems. From Kepler, we sort of know how common these small, compact, sometimes called STIPS systems are, the systems of tightly packed inner planets. Is like Kepler 11 is the prototype. There's 5 planets inside the orbit of Mercury. These are surprisingly common. We know roughly how common Jupiters are from radial velocity surveys. We don't know the overlap. We don't know how often these are in the same systems or if they're completely different. One precludes the other. And this tells us important things about planet formation. In fact, there are predictions that maybe you shouldn't see these ever in the same systems, but we know of at least a couple cases where that's not true, where we see both. And so I'm interested in understanding this overall solar system occurrence and overall architecture rates. We're starting to get a handle on Eta Earth. We know Eta Jupiter. What's Eta Earth given Jupiter? Things like that. And so one of the ways we're going to start learning this in the next couple of years is with TESS. TESS is a MIT-led mission with all the data public to be launched somewhere between March and June of next year, of this year now. And so TESS will look at the entire sky for about a month at a time, observing the whole sky. It's a small telescope, so it'll be a lot of noise on the faintest stars, but there will be data on essentially the entire sky. And for a month, it will observe different patches, and it will take 2 years to cover the entire sky. So that'll tell us about planet occurrence on all the nearby bright stars. Where are in their terminology, where are the best transiting planets? So the small, potentially rocky ones around the nearby stars. These are the stars that we've already observed with radial velocities for 20 years. So we know something about Jupiters in these systems. We're not really sensitive to the Earths yet. But that's kind of the first step to answering this question. And so TESS, from its nature, will have a lot of planets and a lot of false positives. It has very large pixels. There's gonna be a lot of contamination. It's a single filter. In a lot of ways, it's gonna be like the early ground-based transit surveys that found a lot of signals and very few transiting planets. And so, although we've been spoiled from Kepler, a lot of the work on TESS is going to be following up these systems, differentiating the true planets from astrophysical false positives. And so this is a place where SOAR is going to be important, because the first step is understanding the host stars. And so things like the Goodman spectrograph there will be useful just to go out and observe these nearby stars that have planet signals and see, are they actually what we think they are? Are they maybe a G2 star, or is it evolved and actually twice as big as we think it is, so the planet is twice as big, so it's less interesting? Things like that. And then the near-infrared imaging capabilities of it, also to follow up these transits and see, is it a background eclipsing binary that looks very different in the infrared than it does in the optical? And so then once we're pretty sure that it's a planet, the next question is measuring its mass. What's its density? Could it have an atmosphere? Things like that, to say, is this really an Earth-like planet? And so SOAR doesn't really have the instrumentation for that. There's not a PRV instrument there right now, precise radial velocity. But I'm on the Maroon X team here, which is built, this is a spectrograph to be installed at Gemini next year. And so this is really optimized for M dwarfs, for small planets around them, and is ideal for measuring masses of planets around these stars. And so from all of this with TESS, we'll really nail the small planets, and then be able to combine that with radial velocity surveys that know something about Jupiters, and soon Gaia, which will find all the nearby Jupiters, and really understand overall planet occurrence, not just these little bins of A to Earth or A to Jupiter, things like that.
So you said Goodman would be particularly good for host star characterization.
Yeah. Mm-hmm.
How ideal is it? Is a larger telescope better? Is it overkill?
It's kind of in the right range. That for these Kepler stars, Kepler just looked at one patch of the sky that's fairly small and just targeting relatively faint stars. And so for that case, you really need a big, Keck class, one of these 8 or 10 meter telescopes, just to get enough photons to characterize the star well. This is not really the case for TESS. TESS is a 10 centimeter telescope. Kepler was 85 centimeters. And so by its nature, it's looking at 12th magnitude stars instead of 16th magnitude stars. And so kind of the 4 meter class telescopes are really going to shine here. And especially these what I think of as medium resolution, are of order 10,000 spectrographs, are really going to be in high demand for a lot of TESS follow-up.
So you've mentioned a lot of false positive removal and that kind of thing for TESS. How do you see those efforts fitting in with the plans of the TESS team and the working groups and so on, working in those areas?
Yeah, so the TESS team is very well organized in trying to avoid duplication of efforts, which I think is one of the things they learned well from Kepler, where especially K2, where a lot of groups would go, follow up the same interesting system, and then you find 4 papers on the same star. And so they've divided into these working groups. I'm on the Precision Radial Velocity working group right now, part of my efforts with Maroon X. And so there's effort there to avoid duplication. There is also in the stellar characterization. And if I were to be at UNC where I had access to Goodman regularly, I would join that group as well. There's more risk of duplication of efforts in the north, just because there are so many more telescopes up there. That's the southern hemisphere, which TESS will do first. There's I think just because there are fewer telescopes that can go out and do that sort of work, there will be a little less duplication of efforts. And I think a telescope in Chile will be in high demand for that reason. So I think the test team is well organized, but they are focused on the brightest stars, and they're leaving the fainter stars to the community, which is also self-organized in avoiding making sure everyone is doing different things. But I think the direct test team will be they're expecting to be very overworked, and I think that's the correct expectation for them. Hopefully, there'll be a lot of stuff to look at.
Have you done work like this before, like doing stellar characterization for host stars?
Yeah, so we actually led the first catalog of K2 planet candidates. We had 2 papers. The first was identifying the candidates. That paper was led by Dan Foreman-Mackey, and then confirming some of the candidates, as many as we could. That was led by me. They're in early 2015. And so we went through every step of stellar characterization, false positives, looking at archival data, in some cases going out and getting AO to confirm the data, to confirm the systems, and kind of doing every piece of the characterization. At the end, I think we characterized about 20 planets and confirmed 20 planets. So that was the first with K2, and it's kind of understanding how this is all going to work. And a lot of the lessons that we learned have been useful for my collaborators and others in characterizing K2 planets. So yeah, we have all the practice. We have I've led and my students have led papers on radial velocity follow-up of Kepler targets. And so yeah, we have all the pieces ready to go.
So tell us, you could tell us about other efforts, or maybe a little bit more detail. So so your choice, other efforts, or a little bit more detail about going from characterization of these systems to understanding them from an evolutionary point of view.
Yeah.
And also how students would be involved in this. What types of students, what types of levels of projects?
Sure. I'll touch on that, and then we'll move to another project.
Okay.
Yeah, I think this is really a great kind of project for students to get involved in. Partly because that's what I did for my PhD. But there's so much data, and it's all publicly available. Immediately, the concern is risk of getting scooped. But there's just so much, and people are generally sensitive to being aware that someone else is working on a project and not going after that particular star. And so, the test data itself, public, there's some risk. But then all the follow-up work, it's a great way to really get your feet wet if you're an early grad student, to learn, this is how to reduce data from a spectrograph. This is, what we know about stars and what we don't know about stars, based off of, the spectra that we see, and all the inferences that we make, and the assumptions that we make that we believe to be true, and well, where do those actually come from? So I think there's really nice kind of intro grad student projects that are self-contained, and then growing kind of with the data to large population studies for a thesis, looking at overall planet occurrence rates, looking at perhaps how systems change in time. TESS will look at many clusters. Gaia will, near the end of a student's PhD, if they start the next couple of years, Gaia planets will start coming out. And so being able to look at stars in young moving groups and understanding how their planet occurrence is changing as a function of time tells us about planet formation timescales. People are starting to do this with K2 a little bit, looking at hot Jupiters. There's really not enough data yet to say anything strong, but it's coming. And so kind of extending that, and then getting into dynamics. There will be lots of planetary systems where it's hard to measure masses with radial velocities, just because the timescales, the planets are small, or the timescale is long to measure the planets. But you can start seeing things with transit timing variations. And so having computers like the longleaf cluster there would be very useful for things like that. I've done a little bit of this. It's one of the things that I'd really, with a student that's really motivated by the physics of understanding planetary dynamics and tidal forces and how they evolve. I think there's a lot that can be done there, and the computing resources there are suitable for it. So I think there's a lot to be done with students broadly under the TESS umbrella, and then eventually into Plato and WFIRST in the post-TESS era. WFIRST is one that I'm also very excited about. So then another project, to shift gears a little bit, one that I've been really excited about lately is stellar activity. We don't know a whole lot about stellar activity, which is unfortunate because it really precludes a lot of our understanding of planets, both finding the small planets in terms of what stars do on fairly short timescales and how it affects their radial velocity signatures, and also on longer timescales of the actual change in convective blue shift affecting the radial velocity by about 10 meters per second over 10 years if you're the sun. Completely, in that case, it could mask the signal of, say, Jupiter. And so separating out planetary signals from stellar activity signals is a challenge, partly because we don't know what stellar activity can look like. There are so few stars that we have activity cycles measured, and we know their rotation periods, and understand what their star spot coverage and faculae growth and evolution look like. And so now with all of these surveys, we're starting to get a handle on what stellar activity can look like. And so I've been using the Kepler full-frame images to look at activity cycles of sun-like stars in Kepler data. And we found that typically not surprising, the more quickly rotating stars have much more extreme cycles. We can see that the photometric variations are sometimes 20 times that of the sun. So it's actually varying by 2% over its stellar activity cycle. And we can see that slowly rotating stars are dominated by faculae, like the sun. More quickly rotating stars are dominated by spots. And because we know rotation periods of all the stars in Kepler, at some level, then at some level we know their ages. And so we can see how stellar activity is changing as a function of age, of stellar lifetime. And so I led a paper on this in using just the solar type stars fairly narrowly defined in Kepler. And now I have a student here who's extending this to across the main sequence. And Gaia is coming at just the right time because we'll have parallaxes to these stars very shortly. And so we'll know which ones are a little evolved. And we'll have better stellar parameters in theory as well. So we can really see how stellar activity changes across the main sequence. And the goal of this is then, in the distant future, when we have a star with the transiting planets, we can just look at it and say, oh, well, it's this type of star with this type of rotation period. We know the stellar activity signal must look like this. And so anything we see in the RVs that's not that is due to planets or some other astrophysical process, not magnetic activity.
Okay, so we're in the final bit of this here.
Yeah.
Let me give my colleagues a chance here to ask some questions, and then we'll come back to you, and you can ask us questions about anything, facility-related, teaching, whatever you want.
Sounds great.
So how about the room at UNC? Any more questions there? We have a little bit.
You mentioned AO follow-up, and of course you've made great use of the RoboAO system for that. Thank you. The wondering SOAR has, we don't have a high-resolution AO system on there yet, but we hope to eventually. We also have a speckle system which can do high diffraction-limited imaging for most of the test targets itself. Is there anything that would be useful there for your research, or is that you just didn't decide to focus on that area?
Yeah, and I would love to hear more. One of my questions for later was about future of AO on SOAR, so it's great to hear that something's coming along online soon. Yeah, I think a speckle imager would be really useful. I have some experience using Dizzy to look at M-dwarf binaries in young moving groups with Brennan Bowler and some other collaborators, Jenny Skolnick. So we're trying to look at young M-dwarf binaries to measure dynamical masses to understand the mass-luminosity relation at young ages for M-dwarfs, poorly constrained. And so I think both for projects like that and for a lot of test follow-up, a speckle imager could be very powerful. These stars are bright enough to where you can really make use of a 4-meter telescope plus speckle imaging. So I think there's promise there. The nice thing about TESS is that it's a little bit redder. So Kepler was roughly GR and I band, and TESS is RI and Z band. And so, getting a little closer to wavelengths that we can do decent corrections and get, decent speckle imaging, and also, eventually AO is powerful because then we can actually, measure the brightness, the dilution factors in the actual bandpass that we observed in TESS rather than having to extrapolate from the near infrared to the optical. And so we can understand the radii that we infer better from that. So yeah, I think that in general, the answer is yes, that both will be useful, both for this and for other projects.
Do we have any other questions from the committee? Probably time for one more, but if not, okay, so Ben, let's give you a chance. What questions do you have for us?
Yeah, so I have two. One that we just touched on. I'd like to know about the future of AO on SOAR, and kind of the long-term plans for that. And also, I looked a little bit at the clusters, the computing clusters, and couldn't find a whole lot of information on kind of how easy it is to use and to get time on and things like that. And so I'm curious about kind of the realistic expectations of how much time one could get on that.
I can field the cluster question.
I was going to do that. But...
Oh, John, go ahead. Sure.
Okay. Well, so there's a new cluster here at UNC, which is just coming up. I don't know exactly what the specs are, but I can send them to you. And there's a nominal limit of a few 100,000 hours per year per person, but per group, but you can easily get more than that. They don't enforce anything. Basically the idea here is to let you use as much time as you want without interfering with anybody else. So, yeah, you could probably get up to 1 million hours without much problem, I think.
Okay.
Not paying too much money for it.
They're supposed to charge like $1,000 for an added 200,000 service units beyond your default 200,000.
Okay. A service unit,
my group,
CPU hour?
Yeah.
Okay.
They don't actually do that.
But my group ran over 400,000 a year ago, and they ended up not charging us.
Okay.
So.
And so it seems like it's also fairly straightforward. There's not like long queue times that if you need to get something to run, it runs reasonably fast.
My group has never had to wait more than a couple of hours.
Okay, great.
On the AO side, so as I said, there is a speckle imaging system already on the telescope, which works very well. Andrei Tokivinin leads that, although they're using a UNC camera to do it. And that can observe something like 250 targets per night.
Okay.
So that's something that we're thinking of for test follow-up in a RoboAO style, high efficiency, low depth mode. But it can go to longer, deeper depths if you're interested in that. We also have a testbed full natural guide star AO system in the lab at the moment. We need to find a little bit more money to put it on the telescope, and crucially some more time to put it on the telescope. time from my group, not telescope time.
Right.
So that's in the works. And but for tests, honestly, I think the speckle system would do almost everything that the AO system will be able to do, except for the faintest targets. The AO system would get us probably 1.5 to 2 magnitudes deeper on the faintest target. But yeah, we have diffraction limited capabilities. But, I think sounds like it could fit in quite well with what you're thinking about.
Yeah, I think so.
All right.
Yeah, sounds great.
Any other questions from anyone? Okay, well, I'd like to thank you for your time.
Thanks for having me.
It's our pleasure.
Bye.
Bye.
There we go. Okay.
So just really quick before we move on to the next one. So this is Kristen McQuinn. Partly as a service to her, I really want to ask the kind of somewhat pointed question about her ongoing collaboration with her PhD advisor. I'm happy to be the bad guy and ask the mean question, unless somebody else wants to volunteer to be the bad guy and ask the mean question.
We'll leave it to you unless I get all excited for some reason and want to be the bad guy.
But yes, I partly because I want somebody to ask her this question so she realizes what a red flag it is.
I mean, you can ask it in or like we could good cop, bad cop, but I could ask her about her external collaborations and the role that they play, or you can just be more pointed. Why are you still writing all your papers with your PhD advisor? Or we could do both. So let me grab some more scrap paper. And then I'll fire off the link now.
Ready? Is this someone, just the name? Why is she nice?
Because she's an amazing scientist. She's super productive.
Okay, link is fired.
And she was actually on the last and we sunk her because of this.
Did you ask her last year?
We did not ask her last year, and this year I want to ask her point blank.
I get it.
And it would be interesting just to see if she has an answer to it. Maybe there's a reason why, maybe she needs access to a collaboration or data or something that requires it. So, and both years she came up quite high on the list. So if she can get over that hump, then she'd be really high on the list.
Okay.
So it'd be nice to know if there's something that would put her that high. Ben Montet really should know that RoboAO is an optical system, given we published 3 papers together using a RoboAO.
Oh, what did he say?
He said
Here we go.
an optical system.
Hello,
So, Christy, right?
Christy.
Okay. Welcome. Thanks for sharing your time with us today. I figure we'll start with some introductions. I'm Dan Reichert. I'm chairing the search committee this cycle, and my interests are small robotic telescopes, gamma ray bursts originally, but now I'm more interested in the technology of these systems and making them broadly available. And let's go across the bottom there.
I'm Nick Law. I'm interested in time domain astronomy, exoplanets, and instrumentation.
I'm Adrian Erichek. I work on theoretical cosmology.
I'm John Engel. I'm a nuclear theorist on the committee to offer an external perspective.
I'm Chuck Evans, gravitational physics theorist, work on sources of gravitational radiation, and been involved in SOAR for about 20 years.
All right, so I'm going to go through my introductory spiel so you know what we're looking for today. So the primary thing we want to hear from you today is an overview of your vision for a research program here at UNC, organized by research topics that you would tackle in the near future. And so for each topic, we'd like to hear a brief overview of the science and why it's important. Of course, we got a lot of that from your application. So let's also focus on how our resources would fit with your plans. And by resources, I mean our observational facilities, our computational facilities, if that's relevant, and also our people. How would our grad students fit in, our undergrads, postdocs that you may hire? Now, that said, we don't expect you to be an expert on our facilities at this point. So we're hoping that you'll engage us with questions as you go along. We want this to be less of a presentation and more of a conversation where we're here to help you fill in some of the UNC specific details of your vision. So let's spend about 15 minutes on what you envision for a research program here at UNC, and we'll save the final 5 to 10 minutes for follow-up questions, though I hope some of those will be mixed in as well, and questions that you have for us. Sound good?
Sounds great.
Okay.
Well, thank you for the opportunity today. As you know from my application materials, my overall interests are in structure formation and evolution, so how galaxies have formed in the early universe and how they evolve across cosmic time. And my focus is really on low-mass galaxies in the nearby universe as tools to probe structure formation and evolution. So these galaxies are close enough that we can resolve their individual components, their stars, their gas kinematics, their dust, etc., in order to be able to really do detailed studies of baryonic physics. So within that sort of broad category of structure formation evolution, there are really 3 research themes that I am focused on. The first is really bread and butter galaxy evolution. So this is, star formation histories of galaxies, chemical evolution and abundances, stellar feedback, gas kinematics, really sort of detailed baryonic physics. And these dwarf galaxies are really great to study galaxy evolution because they're simpler than more massive systems and let's say spirals or elliptical galaxies. And they're also the most numerous type of galaxies, so you get large samples in the nearby universe. So I've done a lot of work in this regime, and I'm happy to talk about some of the work I've done. On the horizon now is a Sloan 5 program that was recently accepted in October. This is called the Local Volume Mapper, and it's an IFU program that's looking at very nearby dwarfs and somewhat more massive systems to do very detailed spatial resolution studies connecting the ISM, interstellar medium of galaxies, with stellar populations and their overall evolution. So that's sort of in my future, but I'm happy to talk about some of the work I've done in galaxy evolution in general. The second theme of my research is really near-field cosmology and using dwarfs to probe different questions on near-field cosmology. So for quite a long time now, we know from cosmological simulations that a cold dark matter paradigm does really well at representing the universe on large-scale structure of the universe, as well as the properties of massive galaxies. But when it comes to the small mass scales, cosmological simulations with cold dark matter starts to not represent nature as well. And there's some tension between our theory and what nature is showing us. And these discrepancies, for example, there are a couple of different ones that have been really looked at in the last few years, in the last couple of decades. One is the missing satellites problem, where the simulations overproduce the number of low-mass galaxies. And similarly, some of these galaxies that are produced on the simulations have too great a gravitational potential, too large a dark matter halo, too dense of material in the center of these galaxies compared to what we see in nature. And more recently, the simulations suggested a couple of solutions to these decades-old problem, some of which comes in baryonic physics through stellar feedback, some of which comes in alternative dark matter physics, warm dark matter, self-interacting dark matter. But regardless, on the theory side, they're creating this huge, whole host of testable predictions on our understanding of cosmology in the universe. And as an observer of dwarf galaxies, it's kind of a fantastic space to be in because I have the ability to test a lot of the proposed solutions. So there's a whole theme of my research around that area. And then the third area that I'm working in, it's a really exciting area for me. Since the discovery of dwarf galaxies, we've created these catalogs that discovered and classified dwarfs down to about 10 to the 7 solar masses and stars. And there's been this rough floor in mass scale of dwarf galaxies that we know about. And these are really outside the local group. We found some smaller dwarf galaxies that are satellites of the Milky Way. But what I'm talking about are things that are outside the local group, that are isolated, that are star forming, and haven't been sitting in the halo of the Milky Way like some of these very small ultra faint dwarfs have. So we've been looking for smaller galaxies than 10 to the 7 solar masses for quite some time. You know, they're predicted to exist. But we've been, until recently, unable to find very many of them. And there have been some breakthrough discoveries with new observational data and new analysis techniques that we're finally kind of pushing down in that mass scale to say 10 to the 6 solar masses and even below. And I've been leading a lot of work in this arena. We now have 4 or 5 galaxies below 10 to the 6 solar masses that we found. And each of these has been kind of a treasure trove of discoveries because it's such an unexplored parameter space. And I really think this is just the tip of the iceberg. I think that in the coming years with new observing facilities coming online, we're going to be finding more and more of these very small galaxies. And my hope would be that we can push down to almost the atomic cooling limit of what constitutes a system that survived to the present day and is actually a galaxy. Where's that empirical limit?
So let me ask, how did you find these 4 or 5 pushing down the mass limit?
We have found them through their gas. So if one of the biggest data sets that we've used has been the alfalfa data set, which is a survey of about 7,000 square degrees on the sky using the Arecibo telescope in H1. So by having this cosmological volume of H1, we have been able to sort through the data set and find these very low mass systems. And then through follow-up observations in optical, both in imaging and spectroscopy, we've been able to start characterizing their stellar properties and their gas properties and their chemical abundances.
What kind of optical telescope was used for that?
So this leads into a little bit of my future plans and the resources at UNC, but most of these have been in the Northern Hemisphere with Arecibo, and the follow-up, you can find them, once we've found them in the gas, you can go back to something like SDSS, and there's a hint of that there's a galaxy there in the shallow imaging of SDSS. And then a lot of this has been done with collaborators at Indiana University who have institutional access to the WIND telescope. And we've done follow-up imaging at Kitt Peak, optical imaging of the galaxies, and then also some spectroscopy, optical spectroscopy. And some of them that have very low, these very low mass galaxies have a correspondingly very low metallicity. And we've been doing some oxygen-3 direct method oxygen abundances. And some of them are faint enough that we've had to go to bigger telescopes, like the LBT, in order to get enough signal for robust oxygen detections. But the follow-up has been through WIN and imaging and other spectroscopic facilities. And for some of them that end up being close enough or have interesting enough properties, we've pursued additional follow-up from the space in order to characterize their resolved stellar populations and do work around that. So looking ahead, one of the, alfalfa is only sensitive to a little bit below 10 to the 7th, and we've gotten kind of lucky and found a couple below 10 to the 6th. But, in the future, the meerkat and surveys possible meerkat in South Africa will be able to push down even farther in H1. And so part of my vision would be to use meerkat and the data in the H1 to be able to find a more complete lower masses. And the SOAR telescope, also in the Southern Hemisphere, would be an ideal instrument to be able to follow up on these. One of the challenges in a program like this is to be able to have, enough access with enough time and on a quick turnaround to be able to do the follow-up studies, because I would anticipate a fairly large sample of these galaxies being found. And it's not just imaging, but it's also spectroscopy. And SALT would be very valuable as well for some of the fainter systems to go after the oxygen abundance. Some of the really interesting questions of these galaxies are around their chemical abundances. and their chemical evolution. So that's part of what my vision is. So I can talk more about the resources, but I wanted to just pause here for a second because I just threw a lot of information at you. If you've got any questions about my 3 research themes, or you want to talk about any of them in more detail before I kind of delve a little bit more into the resources part of it.
I followed. What about you all? You all have questions?
What's the timeline for Meerkat? I'm not familiar with that instrument.
Yeah, they are already seeing first light. So in the nearest term. And the Meerkat, the H1 component is something that I have some experience with H1, but a lot of the detailed H1 work is through my collaborators. And my expertise comes in through the follow-up on characterizing their stellar properties, the chemical abundances, and the chemical evolution. So the work with Meerkat would definitely be done with external collaborators.
So a question about your collaborations. One thing that really jumps out on your CMV is how much you're still publishing with your PhD advisor. Most of your papers in the past 5 years have him as a second author. Can you clarify your role in this collaboration and how you've been establishing your own independence as a researcher?
Absolutely, it's a great question. Yeah, I've stayed at Minnesota after I finished my PhD as a self-funded postdoc for a number of years. And so, you know, Evan and I continued to work really closely for a long time because I stayed in Minnesota much longer than, I stayed at my PhD granting institution longer than most grad students do. So it was a natural, you know, professional relationship to continue as I'm still at Minnesota. And, you know, Evan and I work really well together. So it's been really great. But there is definitely been, you know, a shift from being a PhD student with Evan to being a more independent researcher and more of a collaborator. So I think that, you know, I could think about going through specific projects, but having stayed at Minnesota, there was definitely a sort of a slower transition into, you know, in roles because we were both still at the same place. But the last, you know, number of projects that since my PhD, I've played a more of a lead role in it, and Evan's been more of a supporting, you know, collaborator, science discussion kind of role in it. The last 2 years that I've been in Texas, it's the roles haven't changed very much. She's still, you know, an active collaborator with me, but I have definitely been leading my own work for a number of years, writing my own proposals, coming up with my own ideas. You know, it's hard to completely separate the work when you've got somebody who you work so well with and overlap in, you know, expertise so nicely. So I would expect and hope that he would continue to collaborate. We'd continue to collaborate together, but I don't see him as being somebody who is driving the ideas that I work on or driving the results either. He's more of a very active and close collaborator. But I think part of it is really just the longevity of how long I stayed in Minnesota. You know, that was, it was just a really great fit for me. I did not want to be moving for a short-term postdoc position, and I was able to successfully fund my own research. Before I graduated, I had about $250,000 in my own grant money, and it just didn't seem to make sense to go and move to work for somebody else when I could fund my own research.
So you've outlined these 3 themes. Maybe we still have a fair amount of time. Maybe we can go back through them, and you could tell us how each of them would tie to UNC facilities and what projects might be good for grad students and PhD or masters or postdocs or undergrads, that kind of thing.
Right, okay. So I started touching a little bit on the 3rd theme already, this sort of unexplored galaxy population, and how I think that the observing facilities, having institutional access to SALT and SOAR would be a really important component to be able to do that follow-up. I know from having, you know, this sort of corollary in the Northern Hemisphere with collaborators in Indiana, that was a really important thing to have. But it also ties back into that first theme I mentioned, which is galaxy evolution. So, you know, you're characterizing, you're probing into this new galaxy population to study their different components. So it isn't just about, it feeds into galaxy, it also feeds into near field cosmology as we're trying to understand the systems. If you focus just on the galaxy evolution part, I have a new paper that I'm almost finished with now that looks at, you know, for example, galactic winds and stellar feedback in dwarf galaxies. And the sample I'm studying is about 10 galaxies in the northern hemisphere with data that I collected from 2 4-meter scopes at Kitt Peak. And I would imagine doing projects similar to that with SOAR, where you're doing H-alpha observations of very low surface brightness ionized gas. The 10 galaxies that I'm about to publish, you know, we had to sit on these for a very long time with the 4-meter telescopes at Kitt Peak. But you're a little limited in you know, how many you can do. But this ties back into some of the questions I have about near field cosmology. You know, stellar feedback is one of the proposed solutions to the problems with cold dark matter in the simulations. And doing things like studying quantified stellar feedback effects and galactic winds in low mass galaxies over a range of targets is really one of the ways that we're going to be able to test and probe these solutions. I'm thinking specifically about the FIRE collaboration and some of their results in stellar feedback. But that would be one example of a project to do with UNC facilities. In addition, the chemical abundance work I think is really critical. If you think about the mass metallicity relationship, there's a very, you know, all of our data points end at a certain metallicity to a certain stellar mass. And that region, I'm really hoping to fill in the mass metallicity relation with a large sample of these low mass galaxies. Excuse me. In addition, the one area that is relatively unexplored, and basically I think this is because of constraints in observing facilities, is the environment of these dwarf galaxies. So one of the benefits of being able to do something where you have a lot of nights on a telescope like SOAR is to be able to map larger areas of the sky around these dwarf galaxies and to also move into satellite systems of more massive galaxies. You need to be able to do very deep observations over larger pieces of the sky. And so I think that that would also be a great project to tackle with something like SOAR.
When you say larger pieces of the sky, how much larger do you need to address?
So I think it depends on the type of association, that galaxy association you're looking at. In some of the dwarf galaxy associations I've studied, it could be, you know, you could be mapping up to, say, 0.5 degree or a degree on the sky. So, you know, with SOAR's field of view, this is going to take a while, but you would be able to do you know, multiple dwarf galaxy associations. Some of these follow along dark matter filaments that you can kind of trace out the gravitational potential of how these structures are forming together. As satellites of, say, you know, a more massive galaxy, I think the area in the sky could potentially be larger, but, you know, I think you'd have to be a little bit smarter about how you tile. In near field cosmology, I think, you know, there's still a role. I've done a lot of work, as you know, from my CV and research statement with space-based facilities. And I think there's going to still be a role for those type of facilities in these projects. I do think that they work really well together with ground-based observations. I don't think that's an either or. I think that's a together part. In particular, I think HST would still be useful for follow-up work on resolved stellar populations. And looking even farther ahead, I think JWST also has a role to play, particularly in probing another science theme in near-field cosmology that I didn't mention was reionization and the role dwarf galaxies play in reionization, which I also think it is something that we could do with JWST. I'm part of an early release science program for JW. I'm one of the science leads on that, so I'm excited about that opportunity as well. But it's not an either or to me. I really do think these facilities work together. In particular, my experience with galaxies at the faint end of the luminosity function, like Leo P, Leoncino, and a new one, Coma P, we've really tied in this detailed investigation from the ground with targeted observations from space. So I think these are really kind of complementary. In terms of resources, one of the things that is driving me to seek out a faculty position is the ability to build a larger research group. As a research scientist, I don't have the same resources to build a group as I would as faculty. I've worked a lot with undergraduate students, and it's been a great experience in many ways. But there are limitations to working with undergraduates, and one of them is primarily the length of time you get to work with the students and their availability to dedicate to research. So there's some limitations there. I would envision having you know, a number of graduate students and a postdoc or 2 postdocs working with me. And I've got some very specific project ideas that I'm happy to discuss, but they fit within these 3 different themes that I've been talking about. But I'd also like to continue to work with undergraduates in my research program. It's been a really successful endeavor, I think, hopefully on both parts, on part of me and the students. So I just want to pause there again to see if you have any questions about that, or if you want me to go into more detail about sort of more specific projects.
Well, one thing I'll comment on is we have some pretty spectacular undergrads here. Being there are a couple large state schools here, but we're kind of the preeminent large state school in North Carolina. We attract some really talented undergrads. So that's great. And of course, we have the grad students as well who do have more time, as you said. But let's see here. We only have a couple minutes left. So let me ask the committee if they have any further questions. Then we'll leave a minute or 2 for you to ask us questions about UNC, anything that may be on your mind.
I want to add just one more thing then before I turn it over, and that is there is a role for computing facilities in my research. I am not a simulator, and I do not need large supercomputers, but a lot of the work that I do is processor intensive, and so while I don't think I have a very deep understanding of your computing facilities, what I do understand seems that there are clusters available, and I would definitely need to make use of computing clusters in order to do some of the computational work in my research.
That's good. And there does not appear to be a problem with availability here at UNC. We do have some pretty nice resources with new ones coming on as well.
Okay.
Anyway, committee, further questions? Okay.
I would like,
go ahead.
Go ahead, Dan, if you've got one.
No. I just thought there weren't any, so I was going to move on. But go ahead.
Just in my notes, the one piece I didn't really get the SOAR connection was your discussion about probing the chemical abundances of these low mass galaxies. Did you have a role for SOAR in mind in that?
I think it depends on the sensitivity levels that we need to get to. If we could do oxygen abundances and spectroscopic observations, that's where I was leading with that. I do know that the larger collecting area of salt might be important for some of the galaxies, but I think it would depend on the target.
All right. Well, let's give you a chance to ask us anything.
Well, I had a great conversation about UNC in general already by phone, but I would be interested in hearing from just generally from different people on the committee, what are some of the common traits that you see in the faculty at UNC that that make a faculty member excel? Like what are the common traits of people that really excel in your department?
Chuck, you want to tackle the most senior? You've been us for years, so maybe there are good things or bad things about this sample that you can relate.
Oh, I don't know. I mean, I think that I don't know how unique it is, but there's a pretty high degree of collegiality in our department, which has been pretty important. You know, it's hard to organize big projects like SOAR and get involved in SALT and other things like that without having colleagues that you and find common ground with. So I found that to be quite pleasing about the university here, the department here. I think that the astronomy group has, over a period of time, chosen to diversify to a large extent rather than concentrate on one area. There are pros and cons behind that, but I think we've done it in a reasonably good way, so that it does give our students a lot of opportunities to try what they're interested in. So I don't know, maybe I've given Nick and Adrian a moment to collect their thoughts, and they can see things that I'm not.
Anything you want to add as our newest additions, Nick and Adrian?
So you should know that we're both coming up for tenure soon. So I think, speaking for myself, I'm very happy here. And the trait I exemplify is one that exemplifies excelling as well, is what I'd like my colleagues to know.
Excellent.
Well,
Okay.
maybe it's useful if there's it's a Department of Physics and Astronomy. So if you're interested in, physics, there's lots of physicists around. There's nuclear people who are interested in astrophysics.
Yeah.
Not everybody takes advantage of that, ability to cross-fertilize, but it can be. It's nice to have.
But we do that in the also as a point example in the astronomy group, because I sort of blur between physics and astronomy, and Adrian does, and Fabian does. So we teach astronomy courses or we teach physics courses.
I'm very happy, and my students are very happy not to really have to define ourselves as either physicists or astronomers, that we can wear both hats as the situation presents itself.
It's a very collegial environment. You're given a lot of support. We want the people who come here, we want to see them excel, doing their own thing, but also when the opportunity arises, we come together and do big things. That's what I like about it. It's not a small program, and it's not, it's not Caltech, right? Where you're one among many. I feel we're just the right size, that we have this great sense of group. Anyway, we are, I'm afraid, out of time. So thank you for your time today.
Thank you for the opportunity. I appreciate it.
Okay. Good day.
Bye.
Bye. Okay. Next up is Alex Delicka-Wagner.
Oh, yes.
And the link.
Alex Delicka-Wagner.
This person
You
right
can ask about the pronunciation too.
Yeah, please. How do you pronounce your last name?
Let's start with that. And let me get this email sent. Here as well. We're halfway through today. Okay, I think we have Alex. Hello. Can you hear us?
Yes, I can hear you.
Okay, and we can hear you too, so that's good. So here's the first tough question of this interview. That is, how do we pronounce your last name?
Great one. how it was originally pronounced is beyond me, but now the Americanized pronunciation is Derlica. So it's Derlica Wagner.
Derlica.
It was probably Czech and probably originated with a J or a G in front of it instead of a D, but now it's Derlica.
Okay. Well, thanks for taking the time to meet with us today. Let's begin with some introductions, and then I'll go through my normal introductory spiel so you know what's expected of you in this interview. Start with myself. I'm Dan Reichert. I'm the chair of the search committee this cycle. My interests are small robotic telescopes, originally gamma ray bursts. Now I focus more on the technology of these systems and adapting it for widespread use. So let's work our way across the bottom of the screen here.
Hi, I'm Nick Law. I work on time domain astronomy, exoplanets, and instrumentation.
I'm Adrienne Erichek. I work on theoretical cosmology.
I'm John Engel. I'm a nuclear physicist, theoretical nuclear physicist.
Chuck Evans worked on gravitational physics theory, modeling sources gravitational radiation, and been involved in the SOAR project for a long time.
Okay. So the primary thing we want to hear from you today is an overview of your vision for a research program here at UNC, organized by research topic that you would tackle, at least in the short term. And for each topic, we'd like to hear a brief overview of the science and why it's important. We, of course, got a fair amount of that from your application, but a little refresher doesn't hurt after reading so many applications. But we should also focus on how our resources that we have here at UNC will fit into those plans. By resources, I mean our observational facilities, computational facilities, if that's relevant, and our people, be it grad students or undergrads or postdocs that you may hire. Now, that said, we don't expect you to be an expert on all of our facilities at this point, so we're hoping that you'll engage us as you go along. We want this to be less of a presentation by you and more of a conversation. In fact, if it's quiet, I'll interrupt you and try to pepper some questions in there to get some conversation going. Think of us as here to help you fill in the UNC-specific details of your vision. So let's spend about 15 minutes on this, and we'll save the final 5 to 10 minutes for follow-up questions by the committee and questions that you undoubtedly have for us. Sound good?
Sounds excellent. Yeah, please feel free to interrupt or jump in if there are any questions or anything is confusing. So my research sort of can be encapsulated in sort of one. The guiding principle is that I'm trying to understand the fundamental nature of dark matter through astrophysical observations. And so we know now from a number of different probes in astrophysics and cosmology that dark matter really dominates the matter content of our universe. It makes up roughly 85% of the matter density, energy density in the universe. And then the total energy density is, of course, dominated by dark energy, which is another component that I'm interested in and I'm involved in, but is not the primary focus of my research. And so the current paradigm for our understanding, cosmological understanding of dark matter, is that dark matter behaves like a cold, collisionless component to the universe. There have been a number of different theoretical motivations from this coming from cosmology and particle physics, or theoretical explanations for what could make up dark matter. And the purpose of my research is really to try and to figure out, to compare these theoretical models of dark matter to the observational properties of the universe, and to explore where, in what types of objects, what kinds of observations, what kinds of experiments can we build that would allow us to test the various different theoretical models of what dark matter could fundamentally be made up of. So one specific area that is very powerful for trying to perform these tests is the dwarf galaxies that surround our Milky Way. So dwarf galaxies are the most prevalent galaxies in the universe. They also tend to be the oldest galaxies, the most chemically pure galaxies, and the most dark matter dominated galaxies. So the dwarf galaxies that we know of around the Milky Way can have hundreds of times more dark matter in them than the normal baryonic matter, which is in the form of stars in these galaxies. And this makes them sort of uniquely positioned in this experimental space because they have enough visible matter for us to be able to trace the distribution and behavior of dark matter in these systems. But they don't have so much dark matter they don't have so much baryonic matter that it appreciably impacts how the dark matter is behaving. Dwarf galaxies are also extremely interesting from galaxy formation and modeling perspectives, since they're believed to be, the primordial building blocks of galaxies, as well as the belief that dwarf galaxies are sort of tracing down to the lower limit in galaxy formation. So essentially, at some point, we expect that due to reionization, due to stellar feedback, you get to a point where you just are unable to retain your baryons in order to form a galaxy. And we believe that dwarf galaxies are approaching that limit. And so the dark matter baryon interplay in dwarf galaxies is really heavily emphasized there. So I'm interested in using dwarf galaxies, specifically the numbers, the abundances of dwarf galaxies, their distributions, along with other ancillary information, such as one thing that I've been looking at recently is stellar streams, which are actually the disrupted components of star clusters and dwarf galaxies. So they're in essence a snapshot of the Milky Way growing through the accretion of smaller galaxies. And I want to use these components to try and understand how dark matter clumps on the smallest scales, which is a direct tracer of the temperature of dark matter. So if dark matter is not completely cold, if it is, for example, moderately warm, so a particle with a rest mass energy of roughly a kilo electron volt, so keV, then it can alter the abundance of the number of dwarf galaxies that you get, because it essentially washes out the primordial density fluctuations in the early universe. And so this is one example of how you can actually probe a fundamental property of the particle physics of dark matter through an astrophysical observation. And so what I've been working on recently is to use large optical surveys. In my case, I'm using the Dark Energy Survey, which is it's a 500-night survey on the 4-meter Blanco telescope at CTIO in Chile that's using the dark energy camera, which is this new large field of view, fully depleted CCD, thick CCD camera that's primarily interested in measuring dark energy, but is also an exceptional survey instrument for studying the local universe. And so with the Dark Energy Survey, I've been leading a program to search for the faintest galaxies around the Milky Way, and to try to, through measuring their abundance and distribution, to try and probe the fundamental properties of dark matter that govern the formation of these smallest galaxies. So my research deals with large survey instruments predominantly, but the role of follow-up from other devoted telescopes has also been extremely important. If we want, I can get into some of the details about how SOAR is important for this, but I'll maybe come back to that a little later, and just say that that both spectroscopic follow-up and time domain follow-up of dwarf galaxies provides important information about the kinematics of stars in these galaxies and the distances to these galaxies. And this is important for being able to trace the both the dark matter content of these galaxies and their distribution in the Milky Way. So the program that I've been working on or focused on recently has been devoted to these small dwarf galaxies, but the exceptional opportunity about large survey programs is that they really provide data that can be used for a wide variety of different scientific investigations. And what I'm interested in doing going forward is to really bring together many different tracers, astrophysical tracers of the fundamental characteristics of dark matter under a collaborative umbrella that is basically built around the upcoming Large Synoptic Survey Telescope. So LSST is going to be a state-of-the-art, it's going to be basically an order of magnitude improvement on DES and other current surveys. It's going to be a rapid cadence survey that views the entire visible sky every 3 nights. It's going to be wider, faster, and deeper than DES, and will essentially allow us to trace the dark matter distribution of the Milky Way and substructure in that distribution out to the virial radius of our galaxy. In addition, it will be exceptional for testing other ways to test different dark matter scenarios. For example, there's been a lot of renewed interest recently about the possibility that compact objects, specifically primordial black holes, may make up some component of dark matter. LSST will be an excellent instrument for performing microlensing studies to search for black holes or other compact objects in the halo of the Milky Way. And as well, it will allow us through proper motions and photometric parallax estimates to give a much better view of the stellar halo and the local stellar component of the Milky Way galaxy, which allows us to also trace the underlying gravitational potential of the Milky Way, search for substructures, and things like that. And so, as I said before, I'm someone who works very much in large surveys. I also work very much in large collaborations surrounding those surveys. So I'm a member of the Dark Energy Survey Collaboration, which is about 500 people. I'm a member of the Dark Energy Science Collaboration within LSST, which is another several hundred person collaboration. And so these large collaborations built around these exceptional data sets really offer the opportunity to build a program to study an area like dark matter where your different tracers are rather varied. And so I'm starting to establish this program now within the Dark Energy Science Collaboration, and I hope to continue that on into the future. So maybe pausing here for a second to ask for sort of general overviews on that kind of program, and then I can get into some of the SOAR specific, components of this.
The questions. Okay, we are ready to the SOAR connection.
Okay, so yeah, so SOAR has already been pretty important for some of the work that we've been doing with these dwarf galaxies. So the key to realize is that these large photometric surveys like DES or LSST or other surveys with the DCAM instrument, which is something else that I'm working on, I've been working on recently, is that with these photometric surveys, you get brightnesses of stars, locations of stars, and proper motions of stars, depending on how good your astrometry is. You're able to get the distance to dwarf galaxies by fitting the distribution, the stellar populations in these dwarf galaxies with specific stellar isochrones that can then give you a distance modulus and a distance to a dwarf galaxy. But this is significantly uncertain due to degeneracies in the ages and metallicities of these stellar populations. So another independent tracer of distance comes from RR Lyrae stars. And in order to detect RR Lyrae stars and measure them, you need much more rapid cadence. than what is provided by the Dark Energy Survey. And so with collaborators in Chile, we've been using SOAR to take high cadence observations and search for aurora Lyrae associated with the new dwarf galaxies that have been discovered by DES. And so it's important. Yeah.
Would LSST's cadence? I mean, I know aurora Lyraes are sub-day, but given enough data, is this stuff that you'd be able to get out of the LSST data set, or do you really need follow up with a dedicated telescope to get this?
Yeah, so the interesting thing about SOAR complementarity, and I'm sure this is a question that you guys are struggling with yourselves at UNC, is sort of what is the role of SOAR in the LSST era, right? These studies that I'm specifically talking about here, this is a connection more to the intervening years, trying to extract as much information as possible out of the pre-LSST era. I think it's a very open question, and it's one that I struggled about preparing for here as far as where the unique capabilities of SOAR come in the era of LSST. Right, so SOAR provides better image quality than LSST will, and it provides spectroscopy, which LSST won't do at all. The issue is that the LSST depth will be such that many of the objects that are being discovered with LSST are just outside of the range of spectroscopy that can be done with SOAR in a reasonable amount of observing time. And so spectroscopy, you could imagine in the LSST era, you could imagine spectroscopy from SOAR being able to get the brightest members of dwarf galaxies. And that can give you information about bulk motions of the dwarfs. And that can tell you about sort of the Milky Way as a system. Unfortunately, SOAR is just not large enough to be able to give you the internal motions of the stars within dwarf galaxies, which is what's really important for it being able to constrain the dark matter content of a dwarf galaxy. And in fact, this is a problem that's much broader than SOAR, right? The capabilities in the Southern Hemisphere for large multi-object spectrographs are just somewhat limited right now. And so, something that I am interested in pursuing, both from the detector side and from the science side, is the building a large multi-object spectroscopic instrument that is, able to do large spectroscopic surveys, follow-up of LSST discovered objects. This is important both for cosmology, for example, getting redshifts of galaxies to understand dark energy, but also for getting, the internal kinematics of stars. The very large telescopes that are coming along have the problem that they all have small fields of view. And so if you want to do global analyses, those really just are not the ideal instruments to do them with. Okay, so sorry, that was a little sidetrack, but so we've been, sorry, is there a question?
Yeah, so when you're looking at the capabilities of SOAR in the LSST era, how do you see how the 8-meter telescopes, for example, fit in? They're also going to be working with faint objects, and yeah, they can collect 4 times more light per unit time. But how do you see? Is it just going to be impossible to do the kind of science you're doing, or does it because of a timescale issue, or is it something that 8 meters could do, or how does that all fit together?
Yeah, so I think it's going to come from, I think in order to do this science, it really builds across several instrumental capabilities. So the 8-meter telescopes are not going to be able to measure internal dispersions of dwarf galaxies near the virial radius of the Milky Way. That's just not, the capability, the time investment would be too large. But for those kinds of systems where the precise location already, you may be able to do that through collaboration with the very large, 30-meter class telescopes. 30-meter class telescopes are not going to be able to give you stellar kinematics for streams of stars, which is something that's very important for constraining the gravitational potential of the Milky Way, or looking for kinematic gaps in stellar streams that could be introduced from collisions with dark matter substructures. This is a topic that's gained some interest over the past few years. For that, an 8-meter class telescope with a large field of view, talking something like upwards of 1 degree field of view, maybe 1.5 degree field of view, is what you would want to be able to get that spectroscopy of stellar distributions around the Milky Way. And so it's a problem that can't be tackled with just one instrument. And this is true of a lot of LSST science, right? LSST is going to be a phenomenal instrument. It's going to increase the statistics that we have on all kinds of objects just by orders of magnitude. But then understanding how we can extract more physical information than is available just from the photometry is something that many areas of science are going to need to be tackling in the next decade. So in the more near term, so SOAR is very important for high cadence observations of Aurora Lyrae. It's important for also deeper follow-up imaging. So right now, DES, is the largest survey of comparable depth. So DES goes down to roughly 24th magnitude in the G and R bands, which are roughly equivalent to the Sloan GNR filters. But DES does that with essentially only 15 minutes of imaging, right? And so we have this very large data set that's very well calibrated photometrically and very well described systematically. So we're able to apply robust statistical algorithms for detecting candidate dwarf galaxies. But in order to really confirm them, we need deeper follow-up imaging. And for that kind of imaging, DCAM with the wide field of view is just, it's unnecessary. It's not a good use of the instrument. And SOAR has really proven to be a great instrument for going deep on these candidate objects that we're discovering. The spectroscopic capabilities of SOAR are also important and are probably more uniquely situated for LSST. We've been largely using the Magellan telescopes for spectroscopy, but you could imagine that this would be another area that SOAR could contribute to. The spectral resolution, I think it's around 5,500 to 6,000 is maybe a bit low, but people have done similar studies with Keck at roughly that resolution. It's something that we haven't done much yet, but is worth considering. So I think I'm running out of time. Probably.
Yeah. I'm supposed to be the clock master here, but I was just listening to what you said. Okay, so let's take our final few minutes and let's see if we have any other questions from the committee, and then we'll give you a chance to ask a question or two. So committee members, anything?
I have one.
Okay.
So I don't think you mentioned the microlensing aspect of your work, and I wasn't quite sure from your research statement what that goes into. I was wondering if you could just give a really short 1-minute summary of if that could work with SOAR.
Yeah. So okay, great. Thank you for reminding me. So we just got 30 nights of DCAM time to do a pilot microlensing survey of the galactic bulge and the LMC. This is sort of a precursor for developing a larger program with LSST. In theory, SOAR could be very, very instrumental for low mass, high cadence, so high cadence observations of low mass compact objects. Right now, we're specifically pushing towards higher mass scales because that's sort of the domain where there is a unique gap in the coverage. And so we haven't thought a whole lot about SOAR and high cadence follow-up for that. The low cadence surveys are able to make use of parallactic changes in the brightness. So actually the geometric change from parallax can introduce wiggles in your otherwise smooth microlensing light curve. And we're hoping to capitalize on that with the lower cadence surveys. But SOAR is the high cadence, if we had high cadence observations with SOAR, that would be able to complement and confirm candidates that might otherwise be lower significance.
So for the brighter objects, every scope high cadence photometry might be useful. for that as well.
Yeah, that looks like a really cool project, by the way, just from what I found on the website. That seems really neat.
Okay, how about you? Do you have any questions for us about UNC or facilities, anything?
So I think as far as, broad sort of research questions, I think I have two. And one is the reverse of the question that I was asking, and sort of where do you see SOAR going in the era of LSST? And how does that connect to sort of your goal with the position that you're hiring into right now?
Well, we're trying to not, we don't want to bias our thinking. And there are all sorts of different branches of astronomy that could do some really interesting connections between LSST and SOAR. And the position isn't necessarily for an LSST connection, but that's clearly heavily on our minds. So we're trying to go into this with an open mind. We've selected a long list of people who we think could make a bridge. I don't know, maybe I should let Nick say something because he's the SOAR user, I'm not. But in general, we're trying to find someone with just a great vision for SOAR moving into the next decade.
Yeah, I'd say SOAR isn't just UNC. We've got it's an active collaboration of multiple institutions and multiple countries, and NOAO is a large participant in SOAR. And so there's a lot of different directions the community wants to go, I think, and it doesn't have to be just one direction that we want to move in. But what we want to make sure is that SOAR has the technical capabilities to really excel in the next decade, and we're moving rapidly in that direction. So that's, there's a lot of things we could address there. LSST being right next door to SOAR is one thing, but also there's a lot of other subjects, as Dan says, which we think SOAR could have interesting things to say about.
And regardless, we're looking for someone who is not only going to do good work, but will play a leadership role in whatever field direction we go into with this hire across the community. And you had a second question?
So the second question is that over the last year, I've sort of started developing a side project in detector development. And I'm wondering if that is something that's of interest to the program, and as far as the opportunity to get sort of clean. So I'll give you a little background. It was a laboratory research and development effort at Fermilab to develop ultra low noise CCDs, and this was primarily for dark matter direct detection experiments. So these are particle physics style experiments. But we now have a detector that gets less than a tenth of an electron in read noise. And so I'm interested in sort of bringing this technology back into the sort of astronomical applications from which the CCDs were taken. And in order to do that, it would sort of require some, it's not very much, but some clean room access and some cryogenic support and stuff like that for doing electronic testing and readout on these kinds of detectors. And then potentially, putting them into instruments and testing them on telescopes and stuff like that. So, and I guess the question is, does the university sort of support this kind of effort, and what kind of facilities are available for that kind of thing?
So yes, the university does, and within the Asteroid group, I'm not going to try to count them on my fingers, but probably about half of us, if not more, have some connection to instrumentation work. We like to describe ourselves as a bunch of ninja instrumentation-alists, where we have an idea, we can go in, quickly develop something. SOAR is great for this, also for putting things on and quickly testing, and then get out and go on to the next thing that we want to do. But I think every one of the Astros with interest in instrumentation does have the appropriate facilities to carry this out. And Nick's, of course, much more of an instrumentalist than I am, so maybe I should let him answer instead of me.
Yeah, the facilities are great. We have a really good machine shop for making things. We have semi-clean room facilities that Chris Clemens uses to make holographic gratings for spectrographs, but we also have full clean room facilities used by physicists in other areas. Because it's a physics and astronomy department, there's a lot of people working in very different areas that need clean rooms and have complicated labs and that kind of thing. So it's definitely something that the department is used to doing, and a lot of us enjoy.
So on that, I'm afraid I have to cut us off because we've gone over. But I hope we were able to answer your questions, and thank you very much for your time today.
Yeah, thank you for your time, and nice to meet everyone.
All right, have a good day.
You too. Bye-bye.
Bye.
Bye.
Okay.
Dan, I have a question.
Yeah.
Any chance we could signal to Matt a 5-minute break?
Yep, I'll do it right now.
Good.
And maybe at the same time, the next person say we might be 10 minutes late.
Yeah. Yep, so go ahead, take your break.
Thank you.
Also go out in the hallway to warm up.
Who do you think was the most impressive of those people?
So I would say who I thought did the best. I was surprised by Brooke. I thought she did really well.
Yeah.
She had a stronger sword connection than I was expecting. Nick is the first one to talk to her about Benjamin, but I was not impressed.
Right.
I was not impressed by Kirsty. I was less impressed with her this year than I was last year.
How come?
Not enough sword connection.
Oh.
The exact kind of vague, no I thought out.
Yeah, I think these are being very useful in terms of, oh, you're gone now. No, someone's there, let's see.
That's all right. Well, you can tell me.
Oh, there you are. Yeah. Yeah. I don't know. I think these are being very useful in terms of seeing how strong their connection is to SOAR, which is perhaps the primary thing that we're looking for. Reading through the applications gave us some ideas and some inklings, but to have them actually presented, a number of them are, today anyway, seem to have SOAR in a very remote support role, which is not exactly what I think we're looking for. I'm not going to say which ones yet. I want to take them all in and ponder it carefully.
Right. Okay, I'll be back in a minute.
I think the other thing is, you're still there, Nick. I think the other thing I'm going to be looking for, probably you as well, is the appropriateness of what they want to do with the size of our telescope. So, how much of a connection, how important is the connection? but also is it a good size fit?
Just a good general capabilities fit. That's why I've been asking questions like, what field of view do we actually need? And when they say more than a degree, there's not much we can do with that.
Yeah, and when they're discussing, well, 8 meters versus 30 meters in this field of view.
Yeah, but at the same time, you have if you have 4 times as much time on SOAR as you do on an 8 meter, you get the same number of photons. So it's not, and given you're competing with the entire world for Gemini time versus many fewer people for Gemini for SOAR time, it's photon for photon on a signal to noise basis. It's not a bad thing to say that you could do on a 4 meter what you can do on an 8 meter.
And the fact that we have so much more time can put us in the same ballpark. I sometimes wonder if the project could be done so much better on an 8 meter. Why isn't it? There's probably demand for the time, but
well, there's also a risk factor. I mean, one of the things I really like about SOAR is I can spend time on things that, I can do 2 things that each have a 50% chance of working out, whereas on Gemini, I have to do 1 thing that has a 90% chance of working out.
I worry about that. Yes, you can do it on SOAR by eating up a lot of time. If it were really that good, you get the 8 meter time to do it.
But
anyway, go ahead.
You can't get the 8 meter time at all if it's too risky a project.
Yeah, I see what you're saying. Okay, I'm just going to send it off to Matt now. In here in a second. Oh crap! I'm out of scrap paper again.
Who's this person?
Matt Bayless. He was an undergrad here.
There he is. Hey, Matt, how you doing?
Hey, good. How are you?
Good. Good to see you again.
Loud. Yeah.
All right. So, I was almost going to say we could skip the introductions, but we have some people who came after your time here. So let's do a round of introductions. You know who I am and you know what my interests are, so I won't bore you with that, but let's go across the bar at the bottom.
Hi, Matt. I'm Nick Law. I think we met last time, and I work on instrumentation, exoplanets, and time domain astronomy.
As you know, I'm Adrienne Erichek. I work on theoretical cosmology.
I'm John Engel. I work in nuclear theory.
Matt, you know me, Chuck Evans, and work in gravity wave sources.
It's not as though I've detailed these or researched too all in detail or anything. So.
Okay, so I'm going to give you my general spiel now, and then we'll hear from you. So the primary thing that we want to hear from you today is an overview of your vision for a research program here at UNC, organized by the topics you want to investigate, at least in the near to medium term. And for each topic, we'd like to hear a brief overview of the science and why that science is important. So we, of course, got a lot of that from the application. So let's also focus on how our resources fit with your plans. And by resources, I mean our observational resources, of course, but also computational resources, if that's relevant, and also our people, be it grad students or undergrads or postdocs you would hire. Now, that said, we don't expect you to be an expert on all of our facilities, though you probably know more than many. But there new things have come along as well since you've been here. So feel free. We encourage you to engage with us as you go along and ask us questions. We want this to be less of a presentation and more of a conversation where we're here to help you fill in some of the UNC-specific details of your vision. So let's spend about 15 minutes on what you envision for a research program here.
You are breaking up a little bit.
Oh, okay. Sorry about that. I'll try to get closer. And can you hear me now?
I think I got most of what.
Okay. And
I can, yeah. It drops for a second every now and then, so I'm getting 90%.
Okay. Well, we can hear you, and you'll do most of the talking. But the key point I was making there is that we hope to make this a conversation as much as the technology permits, I guess. And we'll spend about 15 minutes talking where you'll present your vision to us, and hopefully, we'll have some interaction. And we'll save the final 5 to 10 minutes for follow-up questions by the committee, and we'll try to answer questions that you have about us as well. Sound good? Okay.
Sure. I'll get started. Well, with the guidance of what you wanted to hear about, I have a pretty clear vision for what I would be doing in the first 5-6 year kind of horizon at UNC. I've got kind of 3 distinct research programs that I can break down, and each has its own timeline. They don't entirely overlap, but there's some. All of them are related to my expertise, galaxy cluster astrophysics using strong lensing and lens galaxy studies and galaxy cluster cosmology. And so there's just common threads tying them all together. But most of them are driven by really new, exciting data sets that I have coming in. So that makes it pretty easy to define projects. And one really nice thing with regards to UNC resources and SOAR specifically is that most of these projects have a clear need for like a large ground-based campaign to support the data that we have coming in. So there's a real, particularly about like workhorse instruments, there's like a real lane there. So the first, I guess I'll start with, I have this large Chandra program. It's been a really good year. A lot of data came in for Chandra and in parallel with HST. So there's data that's going to start appearing on disk 3 to 4 months from now. All of it will be on disk by the end of 2019. So it's a really nice time scale for starting up a group to work with that data. It also came with a lot of money, about $500,000 in total. Like 450,000 of that are mine that will go wherever I go. And so it's a really nice seed or nest egg, I guess, for starting up a group and getting the personnel that I need to work on these projects. So this first Chandra program, it's targeting strong lensing selected galaxy clusters with really strong or really high cross sections for strong lensing. The main goals there are to, 1, identify what astrophysics causes these high cross-section systems, and then 2, investigate how they behave in terms of scaling relations, like mass observable scaling relations for the galaxy clusters themselves. So that ties into like cosmology issues with galaxy clusters. That is better calibrating ways to use clusters as a cosmological probe, which will feed into kind of a later project. So this program is really nice. The nice thing about writing a large proposal is that you essentially have already mapped out the papers and thesis level projects that would come from the data. So I already had that for these programs. And my sort of personnel vision needs to start with ideally 1 or 2 grad students and a postdoc, where again, there's already money there to help start with that. And each of those 2 primary goals, the galaxy astrophysics and then the scaling relations cosmology project, would work really nicely as like a core thesis level project for a student. And there's easily more sort of extract from the data there. So that's the sort of broad overview of that program. In terms of supporting data and supporting resources from UNC, SOAR specifically, which I know is of interest to you, there is a lot of HST data coming and coming. There's a lot of Chandra data coming. We have weak lensing imaging from Subaru from years ago, but what we really need is a large ground-based spectroscopy campaign targeting the galaxy cluster members themselves, and where we have Chandra data that will provide cluster medium measurements of the dynamic state of the clusters and hydrostatic masses of the clusters. We have lensing data to measure the total masses on kind of half a megaparsec to megaparsec scales. What we really use is the dynamical measurements to extend maybe even beyond the virial radius. And then also I have an idea to do a really nice sort of complementary observation. Do multi-object spectroscopy that targets cluster members, but then also the central galaxies themselves to measure the stellar velocity dispersions in the core on like tens of parsec scales to constrain the total enclosed gravitational potential in those very small scales. So that'd be a program that would target the entire cluster sample ideally, which is like 30 clusters. This would be 30 nights or so, kind of 3 spectroscopic masks per cluster over the course of 2 to 3 years. So a pretty ambitious campaign, but it's the kind of thing that having access to SOAR would really facilitate. There are other spin-off projects for that that you can ask about, I guess, for the short purpose of brevity. I won't go into detail, but there's also an outlined NSF proposal I've already got together to basically bring in more funding to support that ground-based program and then to start doing joint multi-wavelength analyses with that program. And if that were successful, even grow the group larger. So that's project 1. it needs to start really next year and has a really nice 1 to 3, 4 year horizon as a startup program. The second program overlaps a lot in terms of data. It's using the same strong lensing clusters in many cases, but it's focusing on the lensed galaxies themselves. So the nice thing about having Chandra data on a bunch of strong lensing clusters is that all those clusters also have very highly magnified starburst galaxies behind them. And an idea that's really started to gain a lot of speed, in my mind, and with some people I've been talking with the past couple months, is this idea of doing X-ray observations of lensed galaxies, which has never been done before. But with these highly magnified systems, we can do it in a stacked way using this large Chandra program that I have. And then I actually just wrote a white paper for the Chandra director last month advocating for a DDT call, which they've now issued, which will be a call specifically to grant large chunks of Chandra time to preview like a next generation X-ray telescope science. And turns out there's really nothing Chandra can point at for a megasecond or so that it hasn't already pointed at for 7 megaseconds just in the field. Because X-ray astronomy has been using this instrument for a long time, but lensed galaxies have never really been exploited in this way. So I'm going to be writing a proposal in about 3 weeks, submitting it to get another large chunk of Chandra time and the associated money to go deep on a few of these lensed galaxies. And that's going to be studying the X-ray properties of star formation in high redshift galaxies in a spatially resolved way. The magnification from lensing lets the Chandra PSF actually resolve individual star forming regions where you can start to see supernova remnant and X-ray binary signatures from those star forming regions. That data can be combined with data we already have, a lot of spectroscopy from the ground, HST data, and also this new James Webb spectroscopy that we're going to have coming in about, I guess, 2020 or so. So this Lens Galaxy program will kind of start with the X-ray, but it will also segue by 2020 into this James Webb ERS program that I'm a co-I on. There's a clear, the nice thing about the proposal is my name is attached to several things I'm supposed to deliver as a part of that proposal. And that means that if I were to insert a student into that project, there's a clear lane for that student to work with the data that we have now, and then by 2020 take the James Webb data and start doing fulfilling requirements, I guess, of that project, and really like own a piece of that. And so that's all the sort of larger scale picture there is tying together rest frame optical with James Webb, rest frame UV with Hubble and ground-based spectroscopy, and rest frame X-ray with Chandra to study star formation in a spatially resolved way at high redshift using all wavelength indicators, which I don't think has ever been done in this way before. So that's kind of exciting project number 2. It's it's not as immediate as the cluster astrophysics project, but it's also something where I'd plan to recruit a grad student in year 1 or 2 at UNC. And with the James Webb program, we have to submit a budget by the end of 2018. So I would be able to get money as a part of that to help support the student working on that. So again, there's funding there to kind of lubricate that process. There's not a ton of SOAR overlap with that program in terms of workhorse instruments, but I'm really excited about some capabilities that I don't know as much about. So this is maybe something where you give me some feedback. Specifically, I know there's an IFU and an image slicer capability for Goodman. So spatially resolved rest frame UV spectroscopy from the ground adds really nice information to complement everything else we have. And then the SAMI instrument, this ground layer adaptive optics tool, anywhere that we can improve the spatial resolution that we can get from the ground in the rest frame UV is also really exciting, particularly if you could put like an IFU unit behind SAMI, which I know in theory is something you can do. I don't know if progress has been made to make that happen or not, but it's something that'd be great to do. I know Nick actually has worked with ground layer adaptive optics before, so he maybe even has some expertise that might be relevant here. But anyway, sorry?
GLAO is working very well on SOAR and has been in routine science use for several years now. And you can expect kind of 0.3 to 0.4 arc second resolution from that, full width half max. There is an IFU, the Brazilian CIFS instrument, which is under science verification at the moment. I'm not entirely sure, but I can look it up for you if that's accessible behind the AO system. It probably is not, but I'll have to check on that for you. But there is we do have a Fabry Perot system, which is also under science verification. I don't know if that could push to your the wavelengths you'd be interested in, but that's something you might want to check out, that it can be operated, it is routinely operated behind SAMI and the SAM-AO system. So
Yeah, actually, there was a call for that recently that I saw,
Yeah.
and I was excited. It actually is potentially the nice thing about working with the brightest lens systems is you'd be surprised at how bright some of these things are. Most of the interest here would be emission line diagnostics in the rest frame UV, so emission lines where that helps obviously, and even at the wavelengths where the Fabry Pro works. I mean, I think it would need custom filters. My understanding is it doesn't have that many right now, but like there's carbon 3 1909 of H2 region emission line in the UV and some Wolf-Rayet emission lines that you could target in some of the brightest systems. Hitting 0.35, 0.4 arc seconds would be fantastic because that just, particularly the bluer you can go, the better. Because I mean, we have, Muse is state of the art for doing this kind of thing, but it dies at 5,000 angstroms early, and going bluer than that would be incredibly exciting. I don't think SAMI does that yet, but I think I read in the document there's the potential to upgrade it to do so.
Yeah, I wouldn't count on that, but I think if someone came in really wanting to push that capability, it's something that could happen.
Well, I got excited. Yeah, I have SOAR data from 9 years ago now, I guess, that was just U-band imaging that got down to 0.6 arc seconds naturally. So what got me thinking along the lines, right, that you can start at 0.6 arc seconds, any improvement on that would be amazing. And the real first order goal, particularly going in the rest frame UV, is to kind of match Chandra resolution, and it's about half an arc second, and that you're looking for massive star indicators of both wavelengths. So matching those spatially is really the first order goal. And you're not going to get to James Webb resolution, so that's fine, but take what you can get. But that's great to hear that the GLAO looks good. I think that's a really exciting capability, and I think blue is the thing that SOAR does well, and it's not something a lot of telescopes have these days, going down to like 3200 angstroms. So pushing capabilities that are somewhat rare, like GLAO and blue sensitivity, I think are a smart thing to do in the future. So that's exciting. So in fact, it sounds like there are a lot of SOAR opportunities to supplement the Lens Galaxy program that I'd like to put together. So I did have a third program. If we still have, I guess time's running real short. It's longer term.
We have some extra time since we started late.
So this is a little bit longer term, and it's more on the galaxy cluster cosmology side. So I'm part of the SPT collaboration, and I've been one of their optical and near-infrared follow-up leads for about 5 or 6 years now. SPT SZ was the first generation survey. It finished in 2012. All the great science has come out of it. Its intermediate instrument has been doing a polarization experiment over a small area, so it hasn't really been as interesting for galaxy cluster cosmology. But actually right now they're installing the 3rd generation camera on the telescope, and it will start observing, I guess, this winter South Pole season. It's intended to be a 5-year observing campaign to go about 10 times deeper than the 1st generation survey. So by around 2021, 2022, year 3 or 4 or so, SPT-SE survey data will be kind of mature and ready to go. And that's all millimeter wave imaging of the CMB, against which you identify galaxy clusters as decrements, like shadows. This is going to be a really big project that SPT pushes. We already collaborate closely with DES, and once LSST is online, which should be about the same time scale, those two will be working really nicely together. That is, find cluster candidates with SPT3G, do the optical search in LSST to find counterparts. And that works really well out to redshift 1.1 or so. But where SPT3G gets really exciting, at least from my perspective, is at high redshift. The SPT selection lets you find every cluster of mass. It's like 1 × 10⁻14 at any redshift that it exists. So if there are 10 to the 14 clusters at redshift 3, you'll see them. You will see literally the redshift where they go away. And understanding how the clusters form at those high redshift, these like high density peaks, how they collapse at redshift 2, 2.5, 3, and form massive galaxy clusters is, I think, a lot of interest in the community. Also, using those clusters for cosmological probes is where the SPT really has the potential to start weighing in a significant way, right? Like probing the growth of structure with these galaxy cluster surveys, it's a fairly commonplace thing, but right now it really happens to make it 0 and 1. And extending that lever arm to redshift 2.5 to 3 is where 3G, SPT3G can really start to I think push the envelope on what we can constrain. So calibrating and characterizing those cluster samples at high redshift is important. So this is a project that I'm kind of a natural lead for. I led all the ground-based near-infrared follow-up for SPT-SZ clusters using infrared imager at Magellan. For my first postdoc at Harvard, I did this, and at MIT I've gotten some time too. We've really been trying to figure out how to do this well, because with the current survey, we have tens of clusters at these redshifts, but SPT3G will have about 500 to 600 galaxy clusters that LSST can't see just because the red galaxies get redshifted out of the optical. SOAR has actually a really nice role that it could fill, where we'll have to do a massive first pass near-infrared follow-up campaign, basically like Y and J-band imaging of order 500 things. This is like 50 nights or so over 3 years, ideally, to do a first pass on all the things that appear in SPT3G that we don't see in LSST, which lets us characterize the vast majority of those high redshift clusters. And like some things are beyond the reach of a 4 meter. About redshift somewhere between 1.5 and 2, SOAR will not be able to efficiently find these things. But at that lower redshift end is where the bulk of those 500 to 600 things are. And what you really want to do is weed out the lower Z things among the high Z sample, and then feed your really high Z things into bigger resources, VLT, Magellan, James Webb, ideally. And so there's a really critical campaign that's going to have to take place that could really be carried by SOAR. And that's another project where personnel-wise, it's perfect for a grad student, in that it's a well-defined, observing campaign, a well-defined data set, and it's something that the grad student delivers to the SPT collaboration and really, sort of gains sort of buy-in politically, right, by providing a critical resource. So that's a slightly longer term, not starting in the next 1-2 years, but maybe year 3, 4, 5 from now, that would grow into a really nice thesis level project that I'd like to lead. And I think that pretty much takes me, if I'm getting my timeline straight, to 2024 or 2025, which is as far out as I claim to be able to see the future. But yeah, I think that's more or less my spiel. So I could give executive summaries or answer questions or go back over details that are missing.
Well, let's see if the committee has some follow-up questions for you. Anything? I mean, I think you did a connecting all of these projects to sort of thought through some of the observational details. What about SALT? I mean, SOAR is our primary facility. We also have SALT availability. Where would that come into play? Where SOAR doesn't quite do it.
There's not much of it, right? But
yeah, it's just a little bit.
Yeah, I can't design much of a large program there. I mean, I don't know as much about SALT. I know they have a Fabry Pro capability that might become interesting for the same reasons that like a SAMI Fabry Pro would work, though I don't know if it works as well as you'd want. There will be a big need for spectroscopy for SPT3G, particularly if you can push to higher redshifts, and that's where the big aperture helps. So I don't know that, I mean, there will be programs there. When you're talking with a SPT3G like sample, I don't know that the SALT time available is really a good match to what's going on there, but it's possible. One idea I do have it wasn't anything I described, it would be my seeing the future beyond 2024 thing. In LSST, transients are going to be the name of the game. It was all about this. I don't do a lot of transients these days, but I have really gotten into variable quasars, and particularly strongly lensed quasars where you see multiple images. We've got a couple of these systems where we started doing monitoring campaigns from the ground. LSST would get you that for free. For the best system, we started doing a spectroscopic monitoring campaign. We can do reverberation mapping of each image of the lensed quasar, sort of time delayed, so you actually get different temporal information from each image, and then you also see slightly different lines of sight into the central quasar engine from each image. That's a program that requires, or that would really benefit from something like SALT, just simple multi-object optical spectroscopy with a large aperture so that you can measure quasars when they're brightest and also maybe when they're a magnitude or two fainter on some sort of regular queued timescale. You need maybe an hour, right, every 3 weeks or something. There's a really good potential there, but otherwise there will always be places for follow-up spectroscopy of SPT sources where we can get it. So yeah, SALT, I would never throw away 9 to 10 meter telescope time. I could always find things to do it.
Okay. Let's give you a minute to ask us any questions.
Geez, so a few I had prepared. I guess I got a pretty good answer about SAMI and the GLAO already from Nick, so that was great. I'm curious as to what Okay, well, I'll ask the easy one first. I mean, are there any other upgrade plans in the works for SOAR? I mean, what's the sort of instrument view from the inside there? Is it about new instruments, or upgrading old instruments, or developing software to support existing instruments? Like, what's the...
So a few things. Arcoiris, I never know how to pronounce it. Arcoiris is a triple spec style spectrograph that's going to arrive soon in the next year or so. And so that's near infrared, resolution of about 3000, and a lot of spectral coverage simultaneously. So we're quite excited about that. We have an AO system, a full natural guide star AO system under development here that I suspect will not be able to address anything as faint as you normally work in, but that's something that we're working on at the moment to complement the GLAO wider field system. We're also looking at efficiency upgrades for the telescope, and particularly thinking of LSST. So at the moment we have a telescope operator and things are run by a combination of the observer and the telescope operator. We are looking at semi-automated modes that would allow us to look at a lot more targets each night in kind of low resolution spectroscopy of a lot of targets, that kind of thing. And so improving that efficiency is something that SOAR is actually spending money on at the moment.
That all sounds good. Yeah, I've used triple spec years ago. That's an instrument that would excite me as well for a lot of reasons. Yeah, that would actually be a tremendously powerful tool. Again, it's like even with Lens Galaxies, like emission line stuff on a 4-meter turns out to work out just fine. We've done this.
There are 2 Brazilian instruments which are coming soon, but have been coming soon for a while, so we're not sure when they're going to be available. There's an IFU spectrograph, which it's under science verification, so it's at the instrument telescope and is working, and people are seeing data from it, but it's not been commissioned yet. And then there's a high-resolution spectrograph, Estelis, which will be on the telescope shortly.
Okay, so that kind of feeds into my second question, which was more about SOAR operations. I know remote observing is the big mode. So I'm on the Gemini Users Committee, and I know that there's a big push to generate coordinated transient follow-up for the LSST era, and I'm sure this is something you guys thought about quite a bit. I'm kind of curious as to what the UNC plans are for that. And presumably, I know there's this push to develop this generalized broker system that will allow us schedulable observations and transients across different telescopes, basically a sort of non-specialized system. Is that something? Is SOAR? Is there interest in moving SOAR toward more of a service mode queue split night operating schedule to facilitate?
It's something we've been talking about on the Science Advisory Committee, and the recommendation of the committee was that this should be enabled with pilot programs first, maybe a night a week or something like that, and then moving up to whatever the community decides we need, the SOAR community decides we would like to do for LSST. That's still very much up in the air, and I think this is the time where people are starting to think about it and starting to think how things could happen. So there's been an opportunity to move things in a direction we'd want to move, yeah, that's something that we as a founding partner participate heavily in.
There's also a lot of discussion at the moment around clarifying, modifying our TOO policy. A lot of this was driven by the Kilonova event. And
I heard about that. Yeah.
And we want to be prepared for next time so that there's a way of resolving 20 different requests coming in simultaneously.
Makes a lot of sense. Yeah, I can't sell myself as a gravitational wave astronomer at all, but it's a really big deal here at MIT. There was like a week-long party after that event went up. Yeah. But I mean, I do think that transitioning to more adaptive systems make a lot of sense. I think there's a real lane there where you can in a way, it was putting resources into this, and so I think there's an opportunity to leverage community interest and community resources to upgrade a source system that everyone uses, right? And I know that from the Gemini Users Committee stuff, I know that NOAA has started putting money into developing the system, and I know some of us were pushing to make the system as generalized as possible, so that it wouldn't just be a TOO hey, I have this explosion, let's watch it type of thing, but a tool that would let anyone define certain kinds of basic observations in a very simplified, streamlined way that would, facilitate. It would let you. Would really help to introduce queue type or service type scheduling on any telescope, not just Gemini, but Sora, right? I think it would make a lot of sense, particularly with the remote capability. And a lot of what I do, I mean, pushing a 4 meter, a lot of, you'd always love to be able to classify your science as the stuff that needs the good seeing time versus the stuff that doesn't. And some of the programs I outlined above would really benefit if there were a way to try and optimize which observations are being conducted under which conditions. So I see it's, as I said, I can't sell myself as a transient astronomer, but it's the kind of thing where I try to find ways for all of us to win from the upgrades that community pushes. So I think I see the potential there for SOAR, and it sounds like you guys are thinking about it as well, which is nice.
All right, any final questions by the committee? Not? Okay, it's time to wrap up anyway, so thanks, Matt. Good to see you again.
You too.
Thank you, Matt.
All right, yeah, nice to see you all. Thanks a lot.
Hey, one to go.
Matt,
First name?
Andrew.
Andrew.
Andrew Mann.
Exoplanets.
Yeah, Andrew Mann is next. Well, six in a day is not too painful, I don't think.
Yeah, I think so. Maybe on Friday, could we schedule a 15-minute break ahead of time?
I've already sent them their times, but I'm sure we can. So you want a 15-minute at the halfway point? So I can email again.
I feel like I'm trying not to tune them out after 3 hours of the interviews, I must admit.
I'll try to. I'll email the last three, telling them it could be up to a 15-minute delay.
That sounds great. Thank you.
I just tell them, I just see if there's any objections to just making it a 15-minute.
Okay, I'll do that after this then.
I think it's going really smoothly.
Yeah.
Did you see that Dan Skolnick's on the short list at Pennsylvania?
No, I didn't see. Okay, so we have a cat here. I assume Andrew Mann is behind that cat. Can you hear us, Andrew?
You spoke too soon about it technically going smoothly.
Of course, the problem would be with the internet cat here. Let's see. I'll send an email. Jumped out on his own. Hopefully he'll try again. Yeah, I'm not all surprised about what you say. Okay.
Hey.
We've moved beyond the cat.
Yeah.
And there you are. Okay, great.
You can hear me okay?
Yep.
Yes.
We've been doing this for a couple hours without a technical glitch, and the first technical glitch was a cat from the internet. So.
Of course.
Yep. Okay, good. Welcome, and thank you for spending some time with us today. I think we'll begin with a quick round of introductions, and then I'll give you my opening spiel so you know exactly what we're looking for today.
Okay.
I'll start. I'm Dan Reichert. I'm chairing the search committee this cycle, and my interests are small robotic telescopes, gamma ray bursts as well, but these days I'm more focused on the technology of it and broad scale access to it.
I'm Nick Law. I work on exoplanets and instrumentation and time domain astronomy.
I'm Adrienne Erichek. I work on theoretical cosmology.
I'm John Engel. I work in theoretical nuclear physics.
Chuck Evans, work on gravitational physics theory, the sources of gravitational radiation.
Cool, the full gambit.
Yeah. So let me tell you a little bit about what we're looking for today. The primary thing we want to hear from you today is an overview of your vision for a program here at UNC, organized, broken down by research topic, the things that you'd be most active in over the short and medium term. And for each topic, we'd like to hear an overview of the science and why it's important. But of course, we got a lot of that in your application. So let's also focus on how our UNC-specific resources fit in with your plans. By resources, I mean our observational resources, our computational resources, if that's relevant, and our people, be it grad students or undergrads or postdocs that you would hire. Now, that said, we don't expect you to be an expert on our facilities at this point, so we're hoping that you engage us with questions as you go along. We want this to be more of a conversation and less of a formal presentation, where we're here to help you flesh out and fill in some of the UNC specific details of your vision. So we'll spend about 15 minutes on what you envision for a research group here, and we'll save the final 5 or 10 minutes for follow-up questions and questions that you probably have for us.
Okay, that sounds good.
Okay.
So feel free, by the way, to interrupt with specific questions you have for me. I guess the sort of broad overview of what I work on, I wear 2 hats really, or I like to think of myself that way. One is sort of the STARS end, which focuses on fundamental parameters of young stars and low mass stars. And there's this other hat I wear, which has more to do with exoplanets, specifically young exoplanets. And these are sort of related, but they require different techniques and tools, although they cover similar science areas. So for the STARS work, it's all about getting fundamental parameters out, masses, radii, luminosities, and especially better ages for young stars. And the big picture science applications here are wide-ranging. There's sort of things like if you want to study variations in the initial mass function, you need to be able to convert observables into masses. And this is particularly important for low mass stars because they weigh very heavily on proposed IMF variations, both in the galactic context and in extragalactic contexts. But the main science I want out of this is actually just better fundamental parameters for exoplanet hosts. And so I'm trying to get better radii for hosts of transiting planets so I can get better radii for the planets. This sort of something of a cliche amongst the exoplanet community. You only know your planet as well as you know your star. So my big goal there is just getting really, really good radii and masses for exoplanet hosts. And the main tool I use for doing that, both in the past and going forward, are these systems. We sort of generically call them benchmark stars or touchstone stars. There's a wide range of examples of these. One is just a simple thing like an eclipsing binary, where you can get the radii and mass empirically. It could also be astrometric binaries, where you can monitor the orbit and get a mass, or a star in a young kinematic group, a cluster, an association, a star-forming region, where you know the age of the star because you know the age of the whole cluster through something like main sequence turnoff. So every star within that you assume has the same age. And so you can do things like calibrate how we measure ages of stars. And a lot of this, has focused on, a lot of my past work has focused on doing this on things like M-dwarfs, but I want to move further into young stars specifically, where models are very poor and to complement the young exoplanet work. So models in general do not reproduce well the parameters of young stars, and so this is a a big issue. And in particular, we need better ways to measure ages of stars to get ages of their exoplanets. And, the examples I sort of talked about before, you use a star in a kinematic association, its age, and then you try some technique that you can calibrate. For example, we know for sun-like stars, they rotate faster when they're young and they slow down with time. And so you can calibrate this using stars in these kinds of associations. That's sort of a generically commonly used method now. Going forward, I want to use methods that work better on a broader range of stars, things like isotopic abundance ratios, sort of a wider range of techniques. Now, to get into the sort of details on how we do this in facilities at UNC, the big thing you need here is targets that we get actually from Gaia. Most of what we're getting will come from Gaia automatically. Gaia will provide parallaxes and proper motions sufficient to tag any star to a moving group or association out to distances where we could still study them. And then you just need follow-up to do better characterization of the system. And for that, it's basically just a workhorse spectrograph you need. Something like the Goodman spectrograph is a perfect example, although anything that can go relatively deep, because we're talking about stars in young regions that may be embedded, so they tend to be relatively faint. And I tend to focus on the low mass end, because those stars are more common and they're more important for exoplanets. And so they also tend to be faint, even when they're young. And so something like the Goodman spectrograph works very well for this sort of thing. It also helps that most of the young moving groups are in the south. And so having southern facilities is a real advantage there. So it's just a coincidence that most of the young moving groups happen to be in the south, but it's been an impediment for a lot of observers who only have northern telescope access for doing follow-up. So, in that sense, things like SALT is very powerful for doing this. More longer term, with that sort of work, for things like eclipsing binaries, Goodman actually won't cut it. You need higher resolution spectrographs. But for that, there's things, coming online in the near future, like Stellus. I think that's how that instrument is pronounced. That would be perfect for this sort of work, where we don't need ultra precise RVs, but we need high resolution spectrographs to kind of do this sort of abundance work, stellar chemical abundances for young stars, and radial velocities enough to characterize things like eclipsing binaries. Now that's the stellar end, the stars end for this. And there's sort of a mix of like thesis projects that can go in there, the things I sort of mentioned, getting measuring ages of young stars is sort of its own thesis project, and calibrating techniques to do that. So once we have Gaia parallaxes, but there's also sort of like smaller one-off projects that can be allocated in there. Things like better ages for certain known associations. And I can go into further detail if you want there, but if not, I can talk more about the exoplanet end.
Let's dive into exoplanet.
Okay, so the young exoplanet is sort of the more exciting stuff that's going on. Stars in some ways are interesting, but they're in a lot of ways just the filler for the exoplanet work. So the big science question here is you want to understand how exoplanets change from birth to sort of their mature phase. Most of the exoplanets we know about today are sort of in this mature phase. They're not evolving in significant ways and on observable timescales, with a few exceptions. But in general, most of the exoplanets we know about are in stable systems. So what we want to do is go after a time period where exoplanet evolution is happening very rapidly. Times where the planet may be tens of millions of years old or hundreds of millions of years old or just millions of years old, when evolution is happening at extreme levels. And this could be a wide range of things. This can be atmospheric evolution. I mean, like Earth is sort of a common example. We're not in our first atmosphere. We're probably in our third atmosphere. And so you would want to look at Earth-like analogs, although we wouldn't get an exact Earth analog, when it's 10 million years old and see if it has an atmosphere similar to what we think Earth had when it was 10 million years old. And you can apply that to any of the planets in the solar system or any of the exoplanets we know about today. So how did they get from where they were born to what they are today? That includes atmospheres that I mentioned and migration and structural properties. You can go far enough back in time, you can find planets while they're still colliding with other planets, as we think Earth and many other planets in our solar system did. And you can actually see structural changes because of this. And we want to do this observationally, not just theoretically. And the push is then to find stars in young associations where we can identify planets. And I've been doing some of that with the K2 mission. It just happens to cover a number of young star-forming regions. And using essentially just better computational techniques, we've been able to suss out a number of young planets in these regions using the K2 data. Going forward, though, the next step is naturally TESS and Gaia. So TESS, because it's all sky, covers a lot more young stars than we could previously. And in addition to that, if we can get ages of stars in the field that aren't in these associations from the sort of StarZens of this project, we can apply it to a wide range of existing exoplanets that we don't currently know the ages for. And so then we can apply this on a big set of data. Now, the search for these planets is pretty computationally difficult. The young stars vary quite wildly, and then the noise from these stars tends to be orders of magnitude greater than the signal from the planet. It's just spots and flares, all the typical noise you see in young stars. And so we have to use more complicated methods to get at these, things like Gaussian processes. The technique we're using now is this thing called a notch filter. I won't get too deep into the details, but this is the sort of thing that we want to offload to a cluster, especially since TESS is going to observe millions of stars, although only, order of hundreds of thousands of those are young. That's still far too many stars to run on small computers. It has to be offloaded to a cluster, especially since you're using pretty computationally intensive techniques. And so, my vision would be for UNC, the cluster you have fits this very nicely. It works in very well for this kind of work. Now, some of that is also going to be improving the computational techniques. What we did initially was just sort of wrote something quick to get it out there and do our search so we could start following up the planets. And in the future, I want to really improve the computational speed of these. And that's something the right graduate student would be very valuable in, someone who has more of a computer background and is interested in that sort of computational work. And it could be very interesting for someone who's in that sort of area. But in addition to that, it's not just about sort of finding these planets, it's also about vetting them. And for that sort of work, basically you need two things. One, you need stellar parameters. And again, a workhorse spectrograph is perfect for that. And the second thing you need is ground-based imager to do this vetting for transmission spectroscopy. So what this is you're trying to observe the transit at different wavelengths to get a proxy for its atmosphere. Essentially, the transit is deeper at some wavelengths because the optical depth is different in the atmosphere depending on the molecules that are present. And so you observe the transit at a number of different wavelengths, and you get some measurement of what's going on in the atmosphere of these planets. And test targets are perfect for this. They're nice and bright, but you need a pretty big telescope. You can't just do it with 1 meters to do this sort of thing, to do this sort of follow-up, because you need tons and tons of photons. The size of these effects is tiny fractions of a %. And so you need many tens of millions of photons to measure these effects. And we had actually proposed to do this using SOAR, using the SOAR optical imager in the past. We were weathered out, so I don't have any results for that one. And in going forward, I think that the SOAR optical imager could do this, although it looks like actually Goodman just in imaging mode can do just as well or better for this same sort of thing. And part of this is you're only getting broadband photometry, so you're getting like photometry of the planet, basically. And so it's actually not that great for distinguishing like, oh, there's sodium in this atmosphere, or oh, there's oxygen in this atmosphere. But it is really good for telling the difference between, oh, is this a cloudy atmosphere, or does it have no atmosphere at all? Things like that, big broad stroke differences. But that's really, really important for feeding into James Webb. So that's sort of the next big thing. Webb has instruments specifically designed to do this kind of work, to do transmission spectroscopy. And Webb's going to be really popular. Everyone who does exoplanets is going to want to do atmospheres with Webb because it's going to be so much more powerful than previous methods for doing this. And so essentially the teams that are going to be able to be successful with Webb are those that have, you know, a very interesting science angle, which I think is young exoplanets is a very interesting science angle, and the people who do proper vetting of their targets. There's just too many things you can feed into Webb where you would essentially be wasting the Webb time. You would say, well, you could tell whether this is a cloudy atmosphere on this planet from the ground, so you don't need Webb, come back later. And so you have to do all this pre-vetting first. And again, SALT and SOAR are sort of perfect for these. Most of them can be handled on SOAR, actually. This broadband photometry is sort of a filler program. And so there's sort of basically two different projects here. One is doing the sort of vetting of the young exoplanets we find, checking their atmospheres to see if there are viable Webb targets and which are the best ones to put the best fruit forward, to look at sort of atmospheres of young planets, and then also to use that data to refine the parameters of these systems and do sort of a broader range study on the evolution of these systems. An example would be maybe young exoplanets don't have clouds in their atmospheres, whereas we know older exoplanets do. Or maybe they do have them, which would prove that these clouds are primordial. They form when the planets are very young. And that would be very different than the project you would do with Webb, where you could only follow up maybe 1 or 2 interesting systems, or if you're lucky, 3 or 4. And those would be very, very focused studies where we would pick the best targets out of that larger sample we would do with SOAR, and then follow those up way in depth. And that would be like an in-depth look at one young Neptune or one young super Earth, or if we're very lucky, one young Earth-like planet. So that's sort of that natural path there. And again, those are all, you know, projects that would be great for a student. There's sort of 2 right there. And there's a bunch along the way, and it sort of depends on what we find with TESS and with Gaia for exoplanets, for young exoplanets. And so it's hard to know exactly what will happen, but in general, that's sort of the piece there. And again, you know, SOAR fits that nicely, SALT fits that nicely. There is some other computational work, not just in searching for exoplanets, but in extracting information about the atmosphere from Webb. That also is probably going to require large clusters. You're not going to be able to use, you're not going to be able to just throw James Webb at every wavelength, essentially. You'll have to use certain specific modes where you get out the most information. And what that means is playing around with models of exoplanetary atmospheres and what we think they'll look like when they're young, and trying to see which wavelength ranges are the best. And this is something that needs to be done before we start, you know, going hard on asking for Webb time. Which are the best regions to give you the most information? And this is a pretty complicated optimization problem about which regions extract the most data, and it's a little complicated because you don't really know what to expect when the planets are young. All the models of atmospheres are for old planets, and so you have to make some inferences about what you think the younger planet atmospheres might look like before you can say, well, you know, 2.2 microns or 4 microns, that's the way to go. Any questions about that?
Yeah, this would be a good time to pause and questions from the committee. Well, I'll throw one in there. What about Nick's Everyscope? How might this fit into some of your efforts?
Yeah, so Everyscope is going to be pretty powerful because it covers the whole sky as well, or large regions of the sky. It's going to be pretty powerful on the stellar end, I think. It covers a star-forming region with better cadence and longer baseline than TESS, so it's better at identifying things like eclipsing binaries in these young regions that'll be used for benchmark purposes. I think it's not as strong as things like TESS for exoplanet discovery because of the precision required. But what it's going to be really good for is after you've found the planet, going back and saying, oh, this target, you know, we have a certain amount of baseline, and now that we know where the planet is, maybe we can extract it out of the system, especially if the planet is large enough to get a detection. But for discovery, it's much harder to do this from the ground. In addition, to the fact that the young star is varying, you have the atmosphere and then all your other systematics, and so it's tough to find the young planets from the ground. But once you know they're there, it's really great at going back and better characterizing the star and better characterizing the planet, and also just in general for identifying young stars from variability signatures, from rotation periods. So in that sense, it's actually quite complementary. I didn't want to get too deep in every scope type stuff because I don't know what Nick is already planning, but it's actually it could be quite powerful for this kind of work.
I absolutely agree with everything you said. And man, I wish we had one of these in space. But yeah, and we're always interested in collaborating. There's far more data than we could ever handle sitting on disk. So I have more of a comment than a question that the precision photometry you mentioned with SOAR that you were weathered out from, I can absolutely see why you would go for the SOAR optical imager first when you look at the web pages. But I think you're absolutely right to be thinking of Goodman next time. We've demonstrated 180 parts per million in half an hour with Goodman for transits, and it's been really nice. So yeah, I think that's well worth trying again.
Yeah. So when we did when we actually did the observations, the support astronomer was basically like, "Hey, would you consider switching to Goodman?" And I said no initially. I was like, "No, we already thought about this." But talking it out with them, I think I agree that probably Goodman imaging is going to be best in the end. And we'll probably try that proposal again. I mean, the particular target we were looking at is only visible a narrow window in the year because the transit duration is very long. But so we haven't had a chance to try again, but we will. And so we'll probably do it with Goodman. Although that raises the question of what the optical imager's future is, if you can do almost everything with Goodman, but maybe that's a separate discussion.
I don't think we have time to discuss that right now. But it's amazing when you look at the way Goodman was put together. If you wanted to design a precision photometry machine, you'd end up with something like Goodman, except you would put a grating in the middle of it. And fortunately, you can remove the grating. So
yeah.
So there's a lot of reasons it actually works really well compared to a conventional optical imager.
Okay, any other committee questions? Okay, let's give you an opportunity to ask us questions, whatever's on your mind.
Yeah, so there's a couple instruments with sort of a future that was unclear from perusing the website, and one of them is the Stellus instrument, which sounds from the website like it's ready, but it's not listed in the call for proposal. Do you know what the status is?
So it's my best idea of it is it's sitting at SOAR. They have light down it from calibration sources, but have not yet got photons from the sky down it. But it's something that's it's under active development. It's been under active development for a while, and there have been delays. So it's not clear when it's going to be on Sky, but it's a thing that exists. It's at SOAR. They're working on it actively, and the lab-based calibration images I've seen from SOAR have been actually really nice. So I would be surprised if it wasn't on Sky in the next year.
Oh, okay, that's good. Okay. And the next step up from that one is this instrument Deborah Fisher's building, which I guess is a clone of Express, which is Sorceress. And it sounds like it's unfunded as of right now.
So we just put in an MRI proposal for it, and I say we because UNC is involved in that project, building part of the instrument if we got the funding for it. Sorry, not MRI, MSIP. I think it's a good proposal. We haven't gone through phase 1 yet. We'll hear about that in a couple of months, but it's being actively pushed. And personally, I think it's a no-brainer that we should build it. But we'll see. How proposals go.
Yeah, I mean, it seems like SOAR is the right telescope size and has a nice location for this sort of work, and it sort of seems like a high precision spectrograph is something missing from the instrument list, and so that would be really powerful to use. So
it is a time scale project, and of course the TESS is forefront in the mind there. So if we got the money, it would be something that would be available in the next couple of years.
Okay, yeah, I guess it comes quickly because it's just a clone, right, of Express. So
exactly.
Yeah. So and I've been working with John Brewer here about getting some of our targets onto Express. So that would be nice. I don't do the RV stuff myself, but it's something that I'm sort of interested in. Yeah. So Nick, this is probably another question specifically for you. I noticed the AO capability of SOAR. Almost no one uses it. HRCAM and SAM, they have only a few nights per semester allocated. That's usually a red flag.
So SAM both are actually working very well, but you are right that they're underutilized at the moment. So SAM is starting to push into the extragalactic field with things like the Fabry-Perot instrument that's available for it. HRCAM is something that's been Andrei Tokavinin's kind of baby for a while. We haven't been using it much because the Kepler targets are in the north, and we've been doing other things rather than K2. But when TESS goes up, there's a lot of really obvious and interesting HRCAM things to do. And it is doing 250 targets a night. I've seen the data. It looks fraction limited in the visible on the 4 meter, so it's really nice data. It's really efficient. It's actually, I think you can make a case it's the most efficient instrument on SOAR at the moment, because it's the only one which can do semi-automated observing going from target to target. So it's working very well, and we've actually contributed the science camera for it. They've got a big upgrade for the science camera we've pushed down an extra magnitude in depth. So I think it's something that's poised to come into its own.
Okay, and you do plan on doing RoboAO for SOAR at some point, right?
We do plan on it, but looking at the capabilities of HRCAM, there's a huge amount of science with test targets we can get done before we go to all of the effort of doing the natural guide star system for SOAR, which would allow us to push to the fainter targets, but there's a lot of science we can get out before that.
Okay. Yeah, okay. That could be pretty powerful. I mean, Gaia is going to help a lot because it has pretty good astrometry, but it's not pretty good resolution, but it's not going to be able to do monitoring, and it can't catch really tight binaries. And so I think there's a bright future for that sort of stuff.
Camera, it should, HRCAM should get down to 15th or so with diffraction limited resolution. 14 and a half at least.
Great. Okay. A more general question, is this hire one-off, or are you planning future hires beyond this one, or unknown?
Well, we're always planning future hires. It's a process. We're in the physics department, so we request positions as a department. Sometimes they're in astronomy, sometimes they're in other branches of physics. And sometimes we request by the standard process. Sometimes we try to find ways to short circuit the system and jump ahead with special opportunity hires. We're always trying to grow the group. There is not another one on the books, but the books typically only go 1 year out. So we'll get through this one, and then we'll be looking to the future.
Okay, so just a quick follow-up related to that. Can you give me a little more information on exactly how it works, your relationship with the physics department? It's not, so you're part of it, but I assume there's some autonomous nature to it, or?
Not really. The physics department has a number of groups in it, and we're one of the groups. We get along very well with our physics colleagues. Some of us straddle between astronomy and physics, including Chuck and Adrian here. Also are very much physicists. I mean, we all are at some level, but they're so really. So we work as a unit. We're not separate from the physics department other than we're one of the groups.
Okay.
The only kind of biggest separation I would say is kind of we handle our own course scheduling kind of independently of the rest of the department. So we have an astro curriculum, and it's kind of our job as a group to cover all of our astro classes. And the department mostly leaves us to figure that out in terms of which courses we offer, how we cover them.
You don't all get assigned to teach all the physics classes then?
Some of us want to, and some of us volunteer to.
But normally astro hires who want to teach astronomy get to teach astronomy. We have a wide range of courses, and we're very low-key and flexible at these meetings, trying to accommodate everybody.
Okay.
It's a requirement that some point before, I forget if it's tenure or full professor, but at some point before one of these stages, you have to teach a large lecture section. And that's more of a new requirement of our current chair, and who knows if it will still be there. I can see the arguments as to why that's a good thing. I can also see arguments against, but that's the current policy, that at least one semester you'd be in front of an Astro 101 group.
I don't think that would be a problem. I don't have a lot of experience teaching, but what I have is in front of that sort of class, and I really liked it actually. So you get a lot of questions and a lot of interested people, so that certainly wouldn't be a problem.
All right. Well, we've kind of come to the end of our time, and unless you have any other burning questions.
No, I think that's a good place to stop.
Okay. Well, thank you again for meeting with us today.
All right.
It was move forward quickly.
Nice meeting you all.
Nice meeting you.
Okay, we made it. Halfway there, anyway.
Yeah, I think with the exception of adding the break in the middle, the scheduled break in the middle, this works out to be a reasonable amount to do. Much more, and I think it would have been difficult to keep focused.
Thank you for doing 2 3-hour chunks instead of 1 6-hour chunk.
It's certainly easier than going through all those applications. So.
Yes.
That is true.
Okay, I'll send those 3 emails to the final 3 people on Friday, giving the 15-minute delay. And we don't have to talk about it now, but next time when we're all done or before, we should pick a time. Well, I'll send a when to meet, but we should probably meet early next week if possible. Try to boil this down to a short list. We shouldn't let grass grow in our.
Yeah, I'm at AAS all next week.
All next week. So that begins and ends when?
So I'm back on Friday of next week.
Okay.
And I'm off on the following Tuesday for the rest of the following week.
Is there anybody else on this committee? Or?
UA.
UA.
I think it was should we meet on Saturday after this is done? Saturday or Sunday?
That's
by video. No.
no.
You leave for AAS on Monday?
Sunday.
Sunday.
Yeah. I mean, I could call in from AAS. I'd have to check the scheduling for the exact times I'd be available, but there are an occasional afternoon or something where I can.
Okay, well, let's do the following then. After we have our meeting on Friday, everyone should put together an ordered list and indicate on the list, order the full 12, let's say, but also indicate a go, no go, where you would personally draw the line, and maybe get those to me before you head out to AAS or like early next week. Does that sound reasonable?
Could we plan to meet on that Friday, a week from Friday?
Friday.
I think that's the only one all of us are going to be here for a while.
Okay, so you will be back on the 12th, Nick.
I will be back on the night of the Thursday.
Okay, so we'll plan to meet on the 12th, but in advance of that meeting, so you've earned yourself a reprieve up until the night before. That night before or earlier if you want, send me your lists ordered with a go, no-go line, and I'll put them all together and I'll send them out in advance of our meeting so there's no surprises during the meeting.
I don't feel qualified to make a list, and I'm not going to.
That's okay. That's okay. We appreciate you just being here and observing, making sure we, any advice you can give, and we don't screw anything up diversity-wise either. So the rest of the three of you agree with order by Tuesday the 11th?
Sounds good.
Sounds good.
Okay.
Sure.
Okay, see you Friday.
All right.
So who did you like?
Who did I like?
I'll send out the link to this broadcast right now as well.
It's easier for me to compare within field. So let's pit the exoplanet people and let's see if Nick agrees. But I'll say my opinion before Nick weighs in.
Are we allowed to do this yet, Dan, or should we remain unsullied?
You could discuss. I mean,
Why not?
very low these things.
I would say, with the exoplanet people, I thought Andrew Mann blew Benjamin Montet out of the water. I mean, he's just so much more unique in terms of his focus and exactly how he's going to do it. Whereas Benjamin Montet is like test follow-up, which is what everybody says. And you even tried to draw him out exactly what are you uniquely going to bring to the test follow-up? And I didn't think he answered that terribly compellingly. And then in the head-to-head exoplanet, I would say Mann is the clear winner over Montet. And then the head-to-head galaxy evolution battle, much to my somewhat surprise, because this is not how it was reading the paper applications, I thought Brooke really did a surprisingly good job bringing SOAR in, much better than Christie did.
Mm-hmm.
The Brooke Simmons had a much better SOAR case, more developed SOAR case than Christie did.
She was a lot better than
She was a lot better than I was expecting. Given I didn't think her science would work as well on SOAR, but she had obviously put a lot of thought into it. And she really impressed me with how much SOAR connection she was actually able to come up with that program.
Again, on Extragalactic, I thought Bayliss had a great set of plans.
It's funny, I don't consider Bayliss extragalactic.
I couldn't figure. I had a hard time even understanding what the science was. He just immediately went into instruments and
cluster research.
But what did he want to learn?
So the three different projects. So you're right. He didn't go much into detail about this. Big challenge with clusters is we have a lot more clusters than we have lensing maps for clusters. Mm-hmm. So we need proxies for cluster mass. So when he mentioned scaling relations, that's what he's referring to. We need to know how X-ray emission and galaxy counts scale with total cluster mass. Mm-hmm. And so you need the strong lensing systems to calibrate those.
So what are you trying to learn? Are you trying to learn about dark matter?
You're trying to learn about evolution of structure, so growth of structure through cosmic time, and that really weighs in heavily on dark energy and the relationship in possible modified gravity theories. Mm-hmm. Basically, when did the largest structures form as a function of redshift? And that maps out the entire kind of rare density tail of density fluctuations, and it's a very sensitive probe to both the primordial fluctuations and how those fluctuations develop. And that's really interesting as a probe because it's one of these things where Hubble, the expansion rate, gives us a lock solid prediction for how those structures should grow. And so this is one of the best ways to test for modified gravity because general relativity really predicts, given the expansion rate, you should start to see clusters at this redshift and this redshift and how their abundance should track with time. And
man, I wish he'd said all of that.
Yeah, me too.
I guess he assumed a little more expertise, but yeah, all that is encompassed. All that is folded into he mentioned scaling relations. That's why you care about scaling relations of clusters.
Yes.
You certainly had a lot of thought put into SOAR connections.
Yep. Mm-hmm. Yes.
I really liked Mann. I thought he had an excellent set of plans, and as Adrian says, he was doing something different from the several people we saw on who applied, of just here are the test mission plans, and I will somehow do something nebulous that will help them out. He really had, going for the young stars is a really nice field that he can push into, and he's pushing into it. I really liked his plans, and I thought they'd work really well with SOAR. In terms of getting rapid papers out on SOAR plus science that I absolutely love, I've got to say something for Alex Sterlich-Wagner too. I really thought he had a nice kind of multi-dimensional plan for SOAR in terms of just the nearby. Okay, what we can do on SOAR tomorrow night is look for our Illyria in this, and then what we can do going forward with SOAR. I was a bit concerned about his kind of chauvinistic, don't think there's anything you can do with SOAR in the LSST era.
Right.
That was a bit defeatist.
Yeah, I was disappointed in Alex's presentation. I'm trying to check my notes to remember why.
The only negative I had, I really liked his short-term plans and so on. The only negative was he just said he basically would not have a use for SOAR up relative to stars. He talked about using Spectra for the bright stars. That's what I have in my notes. Yes.
So this last guy, man, who's seemed to be talking mainly about SOAR's, vetting for the Webb telescope. Is that something you think is useful?
It's basically the entire exoplanet community will push to observe maybe 10 Webb targets per year.
Mm-hmm.
So this is vetting all of the most interesting possible planets. I thought he made a very good point that getting to observe one of the teams that observes those 10 targets, you want to do this kind of vetting ahead of time. But it's not kind of the type of vetting where you do a few hundred observations and then you don't publish them or something. Each one of the things he's talking about is a paper in itself. Does the planet have an atmosphere and that kind of thing? And then the really cool targets, they go and they get the Nature papers from doing the James Webb observations. And I think that's a very, sensible way of using this.
I kind of like that. SOAR is going to be a workhorse. It's in some fashion. And it could just be going after hundreds or thousands of targets, measuring the same thing over and over for a population study, or it can be a workhorse to help us find the coolest things ever that will then be pushed up to the big telescopes. And my personal preference is the latter is more interesting.
Yeah, I mean, if you're doing science while you're doing the vetting, rather than just wading through piles of craft, I think that's a really good way of doing it. And he had a nice plan for kind of that multi-tier. While we're vetting to find the best targets for JWST, we can also do the following science with what we're doing.
Now, Alex was the one who had the discussion about the advantages and disadvantages of 8 versus 30 meter to do the science, right? That's what you were discussing, Nick?
Yeah.
And he was asked, what do you see SOAR as being useful for, right?
Yeah.
Seemed like he said you must be grappling with this question of what you could do with SOAR too,
which is fair.
Yeah.
I mean, we are in a landscape where there are much larger telescopes, but we have unique capabilities and a lot of cool things we could do. So, I thought the development that he talked about was not anywhere on his research statement, but that was very interesting to hear about.
The what? Say again?
The detector development that Alex.
Oh yeah.
That was quite interesting.
Mm-hmm. Yeah, I tried to organize them from the bottom of our long list to the top, and the same on Friday. So, as much as scheduling would allow, I had to make some.
I got to run and get some lunch.
All right. Yeah. All right. I'll talk to y'all later.
See you Friday.
Guys.